Step outside on a clear night, somewhere far from the glow of cities, and look up. There it is, that pale, luminous disk hanging in the darkness, so familiar that we often forget to really see it. The moon. It rises over the ocean and bathes the waves in silver. It climbs above mountain ranges and casts long shadows across valleys we have never walked. It has been there for every moment of human history and for billions of years before we existed to notice it at all. You might glance at it for a moment and move on with your evening. But consider this, that serene, silent companion is one of the most profound puzzles in all of science. Where did it come from? How did it get there, orbiting our world with such precision that ancient peoples could set their calendars by its phases? And what does its existence tell us about the violent, chaotic origins of the very ground beneath your feet? These are not idle questions. The moon is not simply a pretty ornament in our night sky. It is a time capsule, a frozen record of events so ancient and so catastrophic that Earth itself has long since erased all evidence of them from its own surface. Our planet has been battered by asteroids, sculpted by volcanic eruptions, reshaped by the relentless movement of tectonic plates, and weathered by 4.5 billion years of wind, rain, and geological upheaval. The earliest chapters of Earth's story have been overwritten, buried, dissolved into the deep mantle. But the moon remembers. And when scientists finally began to piece together the moon's history, they discovered something that rewrote our understanding of how planets form, how life becomes possible, and why we are here at all. The answer involves a collision so violent that it staggers the imagination, a world-ending impact that, paradoxically, made our world what it is today. But we are getting ahead of ourselves. To understand how we came to know the moon's true origin, we need to travel back through history, to a time when that glowing disk in the sky was not a scientific question, but a divine mystery, a god, a goddess, a beacon guiding sailors and shaping the rhythms of human life. For as long as there have been human beings, there has been wonder at the moon. Our ancient ancestors, huddled around fires in the African savanna, watched it wax and wane with the regularity of a heartbeat. They noticed how it rose at different times in different places along the horizon, how its shape changed from a slender crescent to a brilliant full circle and back again. In a world without clocks, without calendars, without any way to measure the passing of time except by the movements of celestial bodies, the moon became humanity's first timekeeper. The Sumerians, who built the first great civilization in Mesopotamia around 3800 BCE, worshipped the moon as the god Nana, also called Sin. To them, Nana was not merely a light in the sky, but a wise and benevolent deity, the father of the sun god Utu and the goddess of love, Ishtar. Nana rode across the heavens each night in a crescent-shaped chariot, his passage marking the boundaries of days and months. The Babylonians, who inherited Sumerian culture, believed that Sin governed wisdom and foresight, that the moon's phases could predict the fortunes of kings and empires. They recorded its movements on clay tablets in cuneiform script, creating some of the earliest astronomical records in human history. When the moon turned blood red during an eclipse, they interpreted it as a warning of disaster. To protect their rulers, they would install substitute kings to absorb the bad omen, sometimes sacrificing these unfortunate stand-ins to appease the heavens. Across the Mediterranean, the ancient Egyptians associated the moon with Thoth, the ibis-headed god of wisdom, writing, and measurement. Thoth was the divine scribe, the keeper of records, the measurer of time itself. It was Thoth who maintained the cosmic balance known as Ma'at, the fundamental order underlying all existence. The Egyptians understood that the moon's cycles were connected to the flooding of the Nile, to the rhythms of agriculture, to the very pulse of life along that great river. Another Egyptian lunar deity, Khonsu, whose name means traveler, was believed to cross the night sky each evening, driving away evil spirits and bringing healing to the sick. In ancient China, the moon carried different meanings but equal reverence. It was associated with yin, the passive feminine force in the cosmic balance with yang. The Chinese told the story of Chang'e, a woman who swallowed an elixir of immortality and ascended to the moon, where she lives to this day in a palace of cold jade. The Mid-Autumn Festival, still celebrated today, honors her tale with mooncakes, lanterns, and family gatherings. For the Chinese, eclipses were not merely astronomical events, but signals from heaven, sometimes interpreted as displeasure at earthly rulers, occasionally leading to dramatic changes in leadership. The ancient Greeks personified the moon as Selene, a beautiful goddess who drove a silver chariot across the darkness, pulled by white horses. Selene fell in love with the mortal shepherd Endymion and asked Zeus to grant him eternal sleep so that she might gaze upon his beauty forever. Her sister Artemis, goddess of the hunt, also came to be associated with the moon, representing purity, wilderness, and the protection of young women. The Romans called their moon goddess Luna, and from her name we derive the word lunar and the old belief that the moon could drive people to madness, hence lunatic. From the Aztecs to the Norse, from the Hindu traditions Chandra to the Lakota Sioux and their sacred moon ceremonies, virtually every human culture has gazed upon that silver disk and seen divinity. The moon governed fertility and harvests. It marked the proper times for planting and reaping. It guided sailors across dark oceans. It was woven into the fabric of human existence in ways so profound that we can barely imagine life without it. But what was it? What was the moon made of? How far away was it? And how did it come to be? For most of human history, these questions belong to the realm of philosophy and religion rather than science. The ancient Greek philosopher Aristotle, whose ideas dominated Western thought for nearly 2,000 years, taught that the heavens were fundamentally different from the earth. In Aristotle's cosmos, our world was the realm of change and corruption, where things came into being and passed away, where matter was composed of 4 elements: earth, water, air, and fire. But the heavens were eternal and unchanging. Celestial bodies were made of a 5th element, the quintessence or ether, a perfect, incorruptible substance unknown on earth. The moon, in this view, was a flawless crystalline sphere, smooth and unblemished, orbiting Earth in perfect circles along with the sun, planets, and stars. This idea of celestial perfection had profound implications. If the heavens were perfect and unchanging, then they were closer to the divine. The earth, with all its imperfections, sat at the center of the universe not as a place of honor, but as the cosmic sewer, the lowest point where all the heavy, corrupt matter had settled. The moon marked the boundary between these 2 realms. Below its sphere was the terrestrial world of flux and decay. Above it was the celestial realm of eternal, immutable perfection. For centuries, philosophers and theologians refined this model. Medieval scholars, combining Aristotelian physics with Christian theology, placed God himself in the outermost heaven, the empyrean, beyond the sphere of the fixed stars. The structure of the cosmos became a religious truth as well as a scientific one. To question it was not merely to propose an alternative theory, but to challenge the divine order of creation. Then came the telescope. In the spring of 1609, Galileo Galilei, a mathematics professor at the University of Padua, heard rumors of a remarkable invention from the Netherlands. Dutch spectacle makers had figured out how to combine lenses in a tube to make distant objects appear closer. Galileo, curious and ambitious, set about building his own version. Through trial and error, he learned the principles of lens grinding and telescope construction. His first attempt magnified objects about 3 times their natural size. Within months, he'd produced instruments that magnified 8 times, then 20 times, then 30 times. Others had built telescopes and pointed them at the sky. The Englishman Thomas Harriot observed the moon through a telescope in July 1609, months before Galileo's first recorded observations. But Harriot was an isolated figure who did not publish his findings or grasp their full significance. Galileo was different. He was a skilled observer, trained in the Renaissance tradition of art as well as science, and he understood how to interpret what he saw. On the evening of November 30th, 1609, Galileo turned his telescope toward the moon. What he observed shattered 2,000 years of philosophical certainty. The moon was not smooth. It was not a perfect sphere of crystalline ether. Its surface was rough and uneven, marked by what Galileo immediately recognized as mountains and valleys, craters and plains. The boundary between light and shadow on the lunar surface, the line astronomers call the terminator, was not a clean arc but a jagged, irregular edge. Peaks caught the sunlight, while neighboring valleys remained in darkness. Galileo, with his artist's eye and understanding of chiaroscuro, the technique of rendering light and shadow, grasped what he was seeing. These were physical features, solid geography, terrain not unlike the landscapes of Earth. He observed the moon over many nights, sketching what he saw with meticulous care. He watched how the pattern of light and shadow changed as the moon moved through its phases, how craters emerged from darkness as the sun crept across the lunar surface, how certain spots remained perpetually bright, even in shadow, suggesting high peaks catching light above the surrounding terrain. He estimated the heights of lunar mountains by measuring the length of their shadows, and calculated that some towered several miles above the surrounding plains, comparable to the Alps or Pyrenees on Earth. Galileo published his findings in March 1610 in a short book titled Sidereus Nuncius, the Starry Messenger. The engravings of the moon that accompanied his text showed a world of striking physical reality, a rocky, cratered surface that bore no resemblance to the perfect Aristotelian sphere. The book caused a sensation. Within weeks, Galileo was famous across Europe, celebrated by some, denounced by others, but impossible to ignore. The implications were staggering. If the moon was not perfect, then the heavens were not fundamentally different from Earth. If celestial bodies could have mountains and valleys, what else might be possible? Galileo's other observations of the moon's orbiting Jupiter, of the phases of Venus, of spots on the supposedly immaculate face of the sun, all pointed in the same direction. The cosmos was not the static, eternal, perfect realm that Aristotle had described. It was a physical universe, subject to the same kinds of processes that shape the world beneath our feet. This was the birth of modern lunar science. For the first time, the moon was not a god or a symbol, but an object of study, a place with geography that could be mapped and analyzed. But Galileo's observations, revolutionary as they were, raised more questions than they answered. What were those craters? What forces had sculpted that rugged terrain? And the most fundamental question of all, where had this world come from? The moon orbits Earth at an average distance of about 384,400 kilometers, close enough that its gravitational pull raises the ocean tides and slows our planet's rotation by a tiny amount each century. It is relatively small, with less than 2% the volume of Earth and barely 1% of its mass. It has no atmosphere to speak of, and temperatures on its surface swing wildly, from minus 233 degrees Celsius in the eternal night of shadowed craters to 123 degrees Celsius under the direct glare of the sun. It is a world of extremes, of silence, of desolation, and yet it is our world's constant companion, locked in an eternal gravitational embrace, its rotation synchronized so perfectly with its orbit that it always shows us the same face. We see the man in the moon, or the rabbit, or whatever pattern our culture has taught us to recognize in the dark patches that ancient astronomers called Maria, Latin for seas, though no water has flowed there for billions of years, if ever. After Galileo, astronomers continued to map the moon with increasingly powerful telescopes. They named its features after scientists and philosophers, its craters bearing the names of Copernicus and Kepler, Tycho and Aristarchus. They measured its size and distance with growing precision, but the question of its origin remained a mystery, a puzzle that would not begin to yield its secrets until the space age brought human beings and their instruments to walk upon its ancient surface. Where did the moon come from? Was it torn from the young Earth in some primordial convulsion? Was it a wanderer captured by our planet's gravity as it drifted through the solar system? Did it form alongside Earth, a sibling world coalescing from the same cloud of gas and dust? For centuries, these questions remained unanswered, the subject of speculation and debate. Then, in the 20th century, we sent robots and astronauts to the moon. We brought back rocks, and in those rocks, we found clues to a story more violent, more dramatic, and more consequential than anyone had imagined. The answer to the moon's origin would rewrite our understanding of Earth itself, revealing that our planet's history began not with gentle accumulation, but with apocalyptic collision. It is a story of destruction and creation, of a world nearly shattered and remade in fire. And it is a story that is still being written, as scientists continue to probe the secrets locked within those 382 kilograms of lunar rock that Apollo astronauts carried home from their journeys to that desolate, luminous world. So let us begin at the beginning. Let us travel back 4.5 billion years to a time when the solar system was young, when planets were still forming from the debris orbiting our newborn sun, and when a collision between worlds would give birth to the moon and change the destiny of Earth forever. For nearly a century before the first astronaut set foot on lunar soil, scientists wrestled with the question of the moon's origin. They proposed theories, defended them passionately, attacked the theories of their rivals, and in the end, every single one of them was wrong. This is the story of how some of the finest scientific minds of their era tried to explain where the moon came from, and how the universe refused to cooperate with their elegant explanations. It is a story worth telling, not because failure is amusing, but because it reveals something important about how science works. Great theories are not born perfect. They emerge from argument, from observation, from the gradual accumulation of evidence that eventually makes certain ideas untenable. The scientists who proposed wrong theories about the moon were not fools. They were working with the limited evidence available to them, applying the best reasoning they could muster. And when their theories fell, it was because new evidence demanded new ideas. The first serious scientific theory of lunar origin came from an unlikely source, the son of the most famous biologist in history. George Howard Darwin was born in 1845 at Down House in Kent, the fifth child of Charles Darwin and his wife Emma. While his father revolutionized biology, George would make his mark in astronomy and geophysics. He became Plumian Professor of Astronomy and Experimental Philosophy at Cambridge, a prestigious position that allowed him to pursue his fascination with the dynamics of the Earth-Moon system. George Darwin understood something that astronomers of his era were just beginning to appreciate. The moon is slowly drifting away from Earth. It was receding, creeping outward at a rate we now know to be about 3.8 centimeters per year. This might seem insignificant, but over geological timescales, it adds up to enormous distances. Darwin realized that if the moon was moving away from Earth, then logically, in the distant past, it must have been much closer. He ran the calculations backward. If you rewound the cosmic clock, tracing the moon's orbit back through billions of years, you would eventually reach a point when the moon and Earth were practically touching. Darwin calculated that at this primordial moment, Earth would have been spinning furiously, completing a rotation in just 5.5 hours. The days would have been barely long enough to notice, a blur of sunrise and sunset as our young world whirled through space. What would happen to a rapidly spinning, semi-molten planet? Darwin proposed that the sun's tidal forces would have created enormous bulges in Earth's viscous mass. As Earth spun, these tidal bulges would have grown increasingly unstable, stretching and distorting the young planet's shape. Eventually, Darwin suggested, the bulge would have become so extreme that a massive chunk of Earth's material was flung off into space. This expelled mass, torn from our planet's body, would have coalesced into the moon. Darwin called this the fission theory, and it had an elegant simplicity that appealed to many scientists of his era. The moon, in this view, was quite literally a child of Earth, born from the spinning body of its parent in a cosmic act of mitosis. But the theory needed physical evidence. Where had this material come from? Someone else soon provided a tantalizing suggestion. The British geologist Osmond Fisher looked at a map of the world and noticed something striking. The Pacific Ocean is enormous, covering nearly half the planet's surface. Fisher proposed that this vast basin was the scar left behind when the moon tore itself free from Earth. "Look at the Pacific," he argued, "and you are looking at the wound from which our satellite was born." It was a poetic idea, and it captured the public imagination. Here was something tangible, something you could point to on a globe and say, "There, that is where the moon came from." By the end of the 19th century, Darwin's fission theory had become the dominant explanation for lunar origins. It seemed to explain why the moon orbits in roughly the same plane as Earth's equator. It accounted for the fact that the moon, while different from Earth in some ways, shares certain fundamental characteristics with our planet. And it had that satisfying Pacific Ocean origin story that made it easy to visualize and explain. But there were problems. Scientists began to run more careful calculations, and the numbers did not quite work out. For the fission to occur, Earth would have needed to spin at truly extraordinary speeds. The angular momentum required to fling off a chunk of material the size of the moon was immense. When physicists calculated how fast Earth would have needed to rotate, they found speeds that seemed implausible. Even more troubling, if Earth had ever spun that fast, the present-day Earth-Moon system should preserve some evidence of that ancient rapid rotation, some fossil of that primordial spin. It did not. Then, in 1930, the British geophysicist Harold Jeffreys delivered what many considered a fatal blow to the fission theory. Jeffreys had actually been one of the theory's strongest proponents in the 1910s, defending it against various criticisms and helping to shore up its scientific credibility. But his continued research led him to an uncomfortable conclusion. The problem was viscosity. If the early Earth had been spinning fast enough to develop an enormous equatorial bulge, that very bulge would have acted as a natural brake, slowing down the rotation before it could reach the speeds necessary for fission. The physics simply did not allow for the extreme spin that Darwin's theory required. Jeffreys, who had once championed the fission hypothesis, became one of its most effective opponents. Coming from a former defender, his criticism carried particular weight. There were other problems too. If the moon had been torn from Earth's outer layers, its composition should closely resemble that of Earth's mantle. While there were similarities, there were also substantial differences that the fission theory could not easily explain. And that Pacific Ocean origin story, compelling as it was, the Pacific Basin is only about 200 million years old, far too young to be the birthplace of a moon that formed over 4 billion years ago. The oceanic crust we see today has been created and destroyed many times over by the relentless churning of plate tectonics. Even as Darwin's theory was crumbling, an alternative had been waiting in the wings since 1909. Thomas Jefferson Jackson. C was by all accounts a difficult man. Born in Missouri in 1866, he showed early promise as an astronomer, earning a doctorate from the University of Berlin and landing positions at some of America's most prestigious observatories. But his career was marked by controversy, conflict, and accusations of plagiarism that followed him throughout his professional life. C had trouble working with colleagues. He was described as peculiar and egotistical, so difficult that the Lowell Observatory fired him in 1898. He ended up at the Mare Island Naval Observatory in California, where he spent the rest of his career in relative obscurity, eventually launching attacks on Einstein's theory of relativity that the physics community largely ignored. But in 1909, C proposed an idea that would outlive his troubled reputation: the capture theory. The capture theory imagined the moon as a wanderer, a rogue body that formed somewhere else in the solar system entirely, drifting through the cosmic void until it happened to pass too close to Earth. Our planet's gravity reached out and snared it, pulling the moon into orbit where it has remained ever since. In this view, the moon was not Earth's child, but a stranger, an immigrant from the outer reaches of the solar system who had been captured and held prisoner by our world's gravitational embrace. The capture theory had certain advantages. It explained why the moon's composition differed from Earth's in various ways. If the moon had formed elsewhere, of course it would be made of different materials. The theory also had a certain dramatic appeal, the image of a wandering world being snared by Earth's gravity and forced into eternal servitude as our satellite. In the 1950s, the capture theory found a powerful champion in Harold Urey, a Nobel Prize-winning chemist who had made fundamental contributions to our understanding of isotopes. Urey believed that the moon was a primitive body, essentially unchanged since the earliest days of the solar system, and that studying it could reveal secrets about how planets formed. His advocacy for a manned lunar landing was driven in part by his desire to test the capture hypothesis. Working with the astronomer Horst Gerstenkorn, Urey developed sophisticated versions of the capture theory that addressed some of the obvious objections. One variant suggested that the moon had formed in an orbit very similar to Earth's, so that when capture occurred, the relative velocities between the two bodies were low enough for gravity to overcome them. But the capture theory had severe problems of its own. The physics of gravitational capture is unforgiving. For Earth to capture a body as large as the moon, the conditions would have had to be extraordinarily precise. The moon would have needed to pass Earth at exactly the right distance, at exactly the right speed, losing exactly the right amount of energy to fall into orbit, rather than simply swinging past and continuing on its way. The probability of such a capture occurring seemed vanishingly small. There was another problem. When astronomers studied the moons of other planets that were clearly captured, such as Saturn's moon Phoebe, they noticed certain characteristics. Captured moons tend to have eccentric elliptical orbits. They often move in the opposite direction from their planet's rotation. They frequently have irregular shapes, looking more like potatoes than spheres. Our moon has none of these characteristics. Its orbit is nearly circular. It moves in the same direction as Earth's rotation. It is almost perfectly spherical. In every way, our moon looks nothing like a captured body should look. While Darwin's fission theory and C's capture theory dominated the debate, a third idea had been circulating since 1873, proposed by the French astronomer and mathematician Édouard Roche. The co-accretion theory, also known as the condensation hypothesis, suggested that the moon and Earth formed together from the same cloud of gas and dust that gave birth to the entire solar system. As the primordial solar nebula collapsed and began to spin, material condensed into the sun and the planets. According to this theory, the moon simply accumulated alongside Earth, a sibling world that formed from the same raw materials at the same time. In the 1950s and 1960s, the co-accretion theory found a powerful advocate in Gerard Kuiper, a Dutch-American astronomer who founded the Lunar and Planetary Laboratory at the University of Arizona, and would later have the Kuiper belt of icy bodies named in his honor. Kuiper showed how some of the problems with the co-accretion theory might be overcome, and his rivalry with Harold Urey over lunar origins became one of the defining scientific debates of the pre-Apollo era. The co-accretion theory had the advantage of simplicity. It did not require any special catastrophic events or improbable captures. The moon and Earth simply formed together, as many other planet-moon systems presumably did throughout the galaxy. It explained why the moon orbits in roughly the same plane as the other planets, and why its composition shares certain similarities with Earth's. But the co-accretion theory had fatal flaws as well. If the moon had formed from the same material as Earth at the same time and place, it should have essentially the same composition. Both bodies would have swept up the same mix of rock and metal from the solar nebula. In particular, the moon should have an iron-rich core comparable to Earth's. But the moon's core is tiny, perhaps only 1 to 3% of its total mass, compared to about 30% for Earth. Our satellite is conspicuously deficient in iron. This was not a minor discrepancy, but a fundamental difference that the co-accretion theory struggled to explain. Why would two bodies forming side by side from the same materials end up with such radically different internal structures? There were other problems. The co-accretion theory could not easily account for the angular momentum of the Earth-Moon system, which is unusually high compared to other planets. And it did not explain certain peculiarities of the moon's orbit and composition that seemed to demand a more dramatic origin story. By the time the 1960s arrived and the space age began in earnest, scientists had reached an impasse. 3 major theories competed for acceptance, and each had serious problems. The fission theory elegantly explained certain similarities between Earth and Moon, but required physically implausible conditions and could not account for the differences in composition. The capture theory explained the compositional differences but demanded an improbable cosmic coincidence and could not explain why the moon's orbit looked nothing like a captured body's should. The co-accretion theory avoided the need for catastrophic events but could not explain why the moon was so deficient in iron or why the Earth-Moon system had such high angular momentum. Harold Urey, writing on the eve of the Apollo 11 mission, titled his review of the situation "The Contending Moons," acknowledging that scientists could not agree on which moon they were actually dealing with. The same observations could be interpreted to support radically different theories. The data was simply insufficient to distinguish between competing hypotheses. This was the state of lunar science as the Saturn V rockets were being prepared for their journeys to the moon. The Apollo program had many goals: political, technological, inspirational. But one of its key scientific objectives was to settle this century-old debate. The rocks that astronauts would bring back from the lunar surface were expected to contain the evidence that would finally reveal how the moon was born. No one expected what those rocks would actually show. When scientists analyzed the 382 kilograms of lunar samples returned by the Apollo missions, they found themselves in an even stranger situation than before. The rocks contained evidence that seemed to support parts of all three theories while also contradicting each one in important ways. The lunar samples were similar enough to Earth rocks to suggest a deep connection between the two bodies. They shared the same oxygen isotope signatures, the blood types that identify where solar system materials originated. This seemed to support either fission or co-accretion, but the samples were also depleted in volatile compounds in ways that none of the theories had predicted. The moon had been, in Urey's phrase, baked somehow, cooked until its water and other volatile materials had boiled away. And there was the enigma of the magma ocean. The Apollo samples contained rocks called anorthosites, light-colored minerals that could only have formed if the moon's entire surface had once been molten, covered in a global ocean of liquid rock. This suggested a tremendously energetic origin, something more dramatic than gentle co-accretion. In the early 1970s, supporters of all three theories struggled to make the Apollo data fit their models. None of them succeeded. The moon, it seemed, had been born through some process that none of the great scientific minds of the previous century had imagined. Fortunately, an overlooked alternative was waiting in the wings, a theory that had been proposed decades earlier and dismissed as too radical to take seriously. It was about to get a second look. We remember Apollo for the footprints and the flags, for Neil Armstrong's words crackling through static, for the grainy television images of astronauts bouncing across an alien landscape. We remember it as a triumph of the Cold War, a demonstration that American technology and determination could achieve what had seemed impossible. We remember it as an adventure, perhaps the greatest adventure in human history. But the true scientific legacy of Apollo was not the footprints. It was not even the experiments the astronauts left behind, though those were valuable. The true legacy was far more humble in appearance: boxes of rocks and bags of dust, carefully sealed and transported back across the void, destined for laboratories where scientists would spend decades extracting their secrets. 382 kilograms. That is what the Apollo astronauts brought home from the moon. It may not sound like much, barely enough to fill a few suitcases. But those 382 kilograms contained the answers to questions that had puzzled scientists for centuries. They contained clues to the moon's origin that would overturn every theory proposed before them. And they contained something else, something unexpected, evidence that the moon and Earth were connected in ways far more intimate and violent than anyone had imagined. This is the story of Apollo's greatest gift, the rocks that rewrote planetary science. The Apollo program's scientific goals were always secondary to its political ones. President John F. Kennedy had not committed the nation to landing on the moon because of a burning desire to understand lunar geology. He did it to demonstrate American technological supremacy in the face of Soviet achievements in space. The scientists who wanted to study the moon had to fight for a place in the program, arguing that if America was going to spend billions of dollars sending humans to another world, it should at least bring back something scientifically useful. They won that argument, though not without difficulty. Sample return became a core mission objective, but the amount of time astronauts could spend collecting rocks was always constrained by other priorities: deploying experiments, taking photographs, planting flags, making phone calls to the president. The first moonwalks were carefully choreographed performances designed as much for television audiences as for science. Still, from the very first moments on the lunar surface, sample collection was paramount. When Neil Armstrong descended the ladder of the lunar module Eagle on July 20, 1969, one of his first actions was to scoop up a handful of lunar soil and stuff it into a pocket on his spacesuit. This was the contingency sample, insurance against the possibility that some emergency might force a rapid departure. If everything went wrong in the next few minutes, at least something would come back to Earth. Everything did not go wrong. Armstrong and Buzz Aldrin spent about 2.5 hours outside the lunar module, and during that time they collected 21.6 kilograms of lunar material. They gathered 50 individual rocks, scooped up samples of the fine-grained regolith, the powdery soil that covers the lunar surface, and hammered 2 core tubes into the ground to collect material from as deep as 13 centimeters below the surface. It was a modest haul by later standards, but it was enough to revolutionize our understanding of the moon. 4 months later, Apollo 12 landed in the Ocean of Storms, returning 34 kilograms of samples, including 45 rocks and core material from as deep as 40 centimeters. The samples were different from Apollo 11's, demonstrating that the moon was not uniform in composition, but varied from place to place. Apollo 13, of course, never reached the lunar surface. Its crew's desperate struggle for survival became the stuff of legend, but from a scientific perspective, it was a painful loss. The Fra Mauro highlands, where they had planned to land, would have provided samples from a completely different type of lunar terrain. Apollo 14 succeeded where Apollo 13 had failed, landing at Fra Mauro in February 1971 and returning 42.8 kilograms of material. Alan Shepard and Edgar Mitchell spent over 9 hours on the surface across 2 moonwalks, using a wheeled cart to carry their tools and samples across the rugged terrain. The final 3 missions were the most ambitious and scientifically productive. They carried a new tool, the Lunar Roving Vehicle, which allowed astronauts to travel far from their landing sites and collect samples from a much wider area. Apollo 15, in July 1971, was the first of these extended missions. Dave Scott and Jim Irwin landed at the base of the Apennine Mountains, one of the most spectacular landscapes on the moon, where towering peaks rose above a vast lava plain cut by a winding channel called Hadley Rille. They brought back 76.7 kilograms of samples, including 370 individual rocks in a deep drill core that penetrated 2.4 meters into the lunar surface. Among their finds was a rock that would become famous, the Genesis Rock. When Scott spotted it on the slopes of Mount Hadley Delta, he immediately recognized its significance. It was a northocite, a light-colored rock composed almost entirely of the mineral plagio class. Its age would eventually be determined at 4.1 billion years, making it one of the oldest rocks ever collected from any planetary body. The Genesis Rock was a piece of the moon's original crust, formed when the lunar surface first solidified from a global ocean of molten rock. Apollo 16, in April 1972, landed in the Descartes Highlands, a region of heavily cratered terrain in the lunar highlands. John Young and Charlie Duke returned 94.3 kilograms of material, including the sample known as Big Muley, at nearly 12 kilograms, the largest single rock brought back from the moon. They also collected anorthosite samples even older than the Genesis rock, some dating back 4.4 billion years. The final mission, Apollo 17 in December 1972, was the crown jewel of the program. Harrison Schmitt, the only professional geologist to walk on the moon, joined Eugene Cernan in the Taurus-Littrow Valley, a site chosen specifically for its geological diversity. They spent more than 22 hours outside their lunar module across 3 moonwalks, covering more than 35 kilometers in their rover and returning 110.4 kilograms of samples, the largest haul of any mission. Schmidt's trained eye proved invaluable. At one stop, he noticed orange soil exposed in a trench, a startling splash of color on the gray lunar surface. This orange soil turned out to be billions of tiny glass beads, ejected in ancient volcanic eruptions and remarkably well preserved in the airless environment. They provided direct evidence of the moon's volcanic past and would later yield surprising insights about water in the lunar interior. When the last astronauts left the moon in December 1972, they had accumulated an unprecedented treasure, 2,200 individual specimens totaling 382 kilograms, collected from 6 different locations across the lunar surface. Nothing like it had ever been attempted, and nothing like it would be done again for more than half a century. But collecting the samples was only the beginning. The real work would happen on Earth. Even before Apollo 11 launched, NASA had prepared for the rock's arrival. The Lunar Receiving Laboratory at the Johnson Space Center in Houston was built at a cost of nearly $8 million, its primary purpose to safely receive and process the samples while also serving as a quarantine facility. In those early days, scientists could not entirely rule out the possibility that lunar material might harbor some form of life or contamination that could pose a threat to Earth's biosphere. The quarantine protocols proved unnecessary. The moon was, as expected, utterly lifeless, and after Apollo 14 the quarantine requirements were dropped. But the need to preserve the samples in pristine condition became, if anything, more urgent as scientists realized what treasures they held. The original Lunar Receiving Laboratory had limitations. It was designed for handling samples from one mission at a time, not for long-term storage of an expanding collection. The vacuum system used to prevent contamination proved troublesome, and scientists argued that a nitrogen atmosphere would be both easier to work with and sufficient to preserve sample integrity. In 1977, construction began on a new facility, the Lunar Sample Laboratory Facility, Building 31N at the Johnson Space Center. Built at a cost of $2.5 million, it opened on July 20, 1979, exactly 10 years after the first moon landing. This 2-story, 1,300 square meter building would become the permanent home of the Apollo samples, designed to protect and preserve them for generations. The facility is a marvel of contamination prevention. The lunar samples are stored and processed in stainless steel glove cabinets purged with high-purity nitrogen gas. The nitrogen atmosphere prevents the samples from reacting with oxygen or moisture, preserving their chemistry in as close to pristine condition as possible. Workers handling pristine samples are separated from the material by 3 layers of gloves, and every tool that touches the samples is meticulously cleaned and tracked. The 382 kilograms of lunar material have been processed into more than 128,000 individually cataloged samples, each with its own identification number and detailed records of its history. About 75% of the collection remains in the main facility in Houston, while a backup collection of roughly 52 kilograms is stored at the White Sands Test Facility in New Mexico, insurance against any catastrophe that might strike Houston. To this day, approximately 500 samples are distributed to researchers around the world each year. More than 50 years after the last astronaut left the moon, scientists are still making discoveries from the Apollo collection, still extracting new secrets from those ancient rocks. When scientists first examined the Apollo samples, they found a world both familiar and strange. The lunar material could be classified into 3 major rock types: basalts, breccias, and highland rocks. Basalts are dark, fine-grained volcanic rocks, similar to the lavas that erupt in Hawaii or Iceland. On the moon, they form the dark Maria, the vast plains visible even to the naked eye from Earth. The Apollo 11 and 12 samples were predominantly basalt, confirming what telescopic observations had suggested. The Maria are ancient lava flows that filled enormous impact basins billions of years ago. But the lunar basalts were different from their terrestrial counterparts, enriched in certain elements and depleted in others, testament to the moon's unique chemical history. Breccias are composite rocks, mixtures of fragments welded together by the heat and pressure of impacts. The moon's surface has been pummeled by meteorites for billions of years, and much of the regolith consists of material that has been broken apart, mixed, and fused back together repeatedly. Breccias provided windows into the moon's violent past, preserving fragments of different rock types that could be separated and studied individually. Highland rocks, particularly the light-colored anorthosites, told a different story. These rocks are composed almost entirely of the mineral plagioclase, a calcium-rich phyllite that forms at relatively low temperatures compared to other minerals. The presence of vast quantities of anorthosite in the lunar highlands suggested something remarkable. Early in its history, the moon's outer layers were entirely molten, covered by a global ocean of magma. In such a magma ocean, minerals would crystallize and separate according to their density. Heavy minerals would sink toward the interior, while lighter minerals like plagioclase would float to the top, forming a crust that eventually solidified into the highlands we see today. This magma ocean hypothesis was one of the major scientific findings to emerge from Apollo, and it required energy sources that none of the pre-Apollo theories of lunar origin could easily provide. The samples also contained surprises at the microscopic level. Within the Apollo rocks, scientists discovered 3 minerals that had never been seen on Earth. The first was armalcolite, a titanium iron magnesium oxide named in honor of the Apollo 11 astronauts, Armstrong, Aldrin, and Collins. With more than 70% titanium dioxide, armalcolite forms only under specific conditions of high temperature and low pressure, providing clues about the volcanic processes that shape the lunar surface. The second was pyrox ferroite, an iron-rich silicate mineral that forms in the late stages of magma crystallization. Its presence indicated that the lunar lavas had cooled and solidified in ways distinct from terrestrial volcanic rocks. The third was tranquilityite, named after the Sea of Tranquility where the Apollo 11 astronauts landed. This zirconium titanium iron silicate became known as the moon's own mineral because, unlike the other two, it was not found on Earth for more than 40 years. Only in 2011 did researchers discover tranquilityite in ancient rocks in Western Australia, confirming that even this last lunar holdout had a terrestrial counterpart. The discovery of these new minerals was scientifically valuable, but it was the broader chemical analysis that proved truly revolutionary. When scientists measured the oxygen isotope ratios in the lunar samples, they received a shock. Isotopes are forms of an element with different atomic masses, and their ratios serve as fingerprints that identify where materials originated in the solar system. Different planets and asteroids have distinct isotopic signatures, reflecting the conditions in the solar nebula where they formed. The moon's oxygen isotopes were virtually identical to Earth's. This was not what any of the pre-Apollo theories predicted. If the moon had been captured from elsewhere in the solar system, its isotopic signature should be different, perhaps radically so. If it had formed independently alongside Earth from the same nebular material, the signatures might be similar but not identical. Instead, the moon and Earth appeared to be made from the exact same material, as if they had been thoroughly mixed at some point in the past. There was another puzzle, equally confounding. The Apollo samples appeared to be completely, utterly dry. Scientists found no water, no hydrated minerals, no evidence that liquid water had ever existed on the lunar surface. The rocks contained far less of the volatile compounds like water, sodium, and potassium that are common in terrestrial rocks. This extreme dryness was actually consistent with one scenario: a catastrophically hot origin that would have boiled away all volatile compounds. But what kind of event could have generated such extreme heat while also thoroughly mixing material from the moon and Earth? The Apollo samples had revealed their secrets, but those secrets were paradoxical. The moon was similar enough to Earth to suggest an intimate connection, yet different enough to rule out simple co-formation. It had been hot enough to form a global magma ocean, yet the pre-Apollo theories had no mechanism to generate such heat. It was dry in a way that suggested violent processing at extreme temperatures. None of the existing theories could explain all of these observations. The fission theory, the capture theory, the co-accretion theory, all failed when confronted with the actual composition of lunar rocks. Something else had happened, something more violent and more complex than anyone had imagined. The answer was waiting, had actually been proposed decades earlier, but it would take the Apollo evidence to finally bring it into the light. The 382 kilograms of moon rocks had done their job. They had shown scientists that every theory they believed was wrong. Now it was time to find out what was right. The idea that would eventually solve the mystery of the moon's origin was born not in a moment of eureka, but in the slow accumulation of evidence and the courage to propose something that seemed almost too violent to be true. In 1974, a year after the last Apollo astronauts returned to Earth, two young planetary scientists at the University of Arizona found themselves wrestling with a fundamental problem. William Hartmann and Donald Davis had been studying the scarred surfaces of Mercury, Mars, and the Moon itself, cataloging the impact craters that pockmarked these ancient landscapes. What they saw told a story of unimaginable violence. The early solar system had been a shooting gallery, with planetesimals of all sizes careening through space, colliding with one another, building up the planets through repeated impacts. Hartmann, who was also an accomplished artist with a gift for visualizing cosmic events, had been a graduate student under Gerard Kuiper, the legendary planetary scientist who founded the Lunar and Planetary Laboratory at Arizona. He had spent years mapping craters on the Moon, including helping to discover the enormous Mare Orientale impact basin. Davis was a dynamicist, skilled in the mathematics of celestial mechanics. Together, they began asking a question that would change everything. If the young planets had been bombarded by countless small objects, they must also have been struck by larger ones. And if the process of planet formation involved objects gradually accumulating into bigger and bigger bodies, then there must have been a time when multiple large bodies existed in similar orbits, not yet swept up into the final planetary configurations we see today. What would happen, they wondered, if two such bodies collided? In a landmark paper presented at a Cornell University conference in August 1974 and published in 1975, Hartmann and Davis proposed something audacious. They suggested that the Moon had formed from debris ejected when a massive object, perhaps the size of Mars, slammed into the young Earth. The impact would have been powerful enough to splash material from both bodies into orbit around Earth, where it would gradually coalesce into the Moon. At the same conference, another pair of scientists, Alistair Cameron and William Ward at Harvard, independently presented a similar idea. Cameron, one of the foremost astrophysicists of his generation, had come to the same conclusion through different reasoning. The fact that two groups arrived at the giant impact hypothesis simultaneously suggested that the idea's time had come. But scientific revolutions do not happen overnight. The giant impact hypothesis faced formidable resistance. For much of the 20th century, geology and planetary science had been dominated by a philosophy called uniformitarianism, the idea that the processes shaping planets operate slowly and gradually, that the present is the key to the past. This view had triumphed over the older catastrophism of scientists like Georges Cuvier, who had attributed major changes in Earth's history to sudden, violent events. The victory of uniformitarianism was so complete that many scientists had an almost instinctive aversion to catastrophic explanations. The giant impact hypothesis was catastrophism on an unprecedented scale. It proposed that the Moon, that serene silver disk, was born in an apocalyptic collision that would have vaporized continents, melted the entire surface of the Earth, and blasted trillions of tons of rock into space. To scientists trained to think in terms of gradual processes, this seemed extravagant, even fantastical. As Hartmann later recalled, colleagues told him that they should exhaust every other possibility first, because the giant impact idea was too outlandish. Some respected scientists simply dismissed the idea without serious consideration, uncomfortable with invoking such violence to explain something as familiar and peaceful-looking as the Moon. The scientific community was not ready to accept that something so cataclysmic had played such a crucial role in making Earth and its Moon what they are today. But Hartmann and Davis were not deterred. They recognized that the impact hypothesis had explanatory power that the older theories lacked. It could explain why the moon was depleted in iron. The impactor's iron core would have merged with Earth's core, while the debris disk that formed the moon consisted primarily of mantle material from both bodies. It could explain the moon's dryness. The extreme heat of the impact would have vaporized water and other volatile compounds, driving them off into space. And it could explain the angular momentum of the Earth-Moon system, the total rotational energy contained in both Earth's spin and the moon's orbital motion. Yet the evidence kept pointing toward exactly that conclusion. Let us paint a portrait of the world that died to give us our moon. Theia, named after the Titan goddess who in Greek mythology gave birth to Selene, the moon goddess, was a protoplanet that formed in the earliest days of the solar system, approximately 4.5 billion years ago. At that time, the region around the Sun that would become the inner solar system was a chaotic place. The solar nebula, the disk of gas and dust surrounding the young Sun, was collapsing, cooling, and condensing. Countless small bodies were forming, colliding, breaking apart, and merging into larger objects. Current models suggest that Theia grew to roughly the size of Mars, containing perhaps 10% of Earth's mass. But where did it form? One of the most intriguing possibilities is that Theia originated at one of the stable Lagrange points in Earth's orbit, specifically the L4 or L5 points, positions where the gravitational pull of the Sun and Earth balance in such a way that small objects can remain in stable orbits, leading or trailing Earth by about 60 degrees. We see evidence for this kind of orbital arrangement today. Jupiter's Trojan asteroids occupy similar positions in Jupiter's orbit, thousands of rocky bodies trapped at the L4 and L5 points for billions of years. Perhaps Theia was Earth's Trojan, a planetary embryo that grew alongside our world in the same orbit around the Sun. But stable orbits can become unstable. As Theia grew larger, its gravitational influence increased. Small perturbations from Jupiter and other forming planets, the gradual dissipation of the remaining gas in the solar nebula, and the gravitational interactions with other planetesimals all conspired to destabilize Theia's orbit. It began to wander. The gravitational dynamics of the early solar system were unforgiving. Once Theia's orbit became eccentric, crossing paths with Earth's trajectory, a collision was not just possible, but probable. Over thousands or millions of years, the two bodies drew closer with each orbital passage, their mutual gravity tugging at each other until the fateful day arrived. Theia came in at approximately 25,000 miles per hour, roughly 40,000 kilometers per hour. The impact was not head-on but oblique, a glancing blow at an angle of roughly 45 degrees. This angle was crucial. A direct hit might have destroyed both bodies entirely, scattering debris throughout the inner solar system without forming a moon. A more grazing impact might have allowed Theia to survive, perhaps going on to strike Earth again later or escaping into a separate orbit. The oblique angle was, in a sense, perfectly tuned to create the outcome we observe. Enough energy to eject vast quantities of debris, but not so much that the debris escaped Earth's gravity entirely. Enough violence to thoroughly process the material, but not so much that no coherent moon could form. For decades, scientists could only imagine what this collision looked like. They could calculate the basic physics, estimate the energies involved, and make educated guesses about the aftermath. But the detailed dynamics of such an impact, how material would flow, fragment, vaporize, and recombine, were beyond the reach of pencil and paper calculations. But in the 1990s and 2000s, a planetary scientist named Robin Canup at the Southwest Research Institute in Boulder, Colorado, began running sophisticated computer simulations that brought the impact to life. Canup, who had been fascinated by the origins of moons since her graduate work at the University of Colorado, developed numerical models that tracked the behavior of millions of particles representing chunks of rock and iron under the extreme conditions of a planetary collision. Her simulations, using a technique called smooth particle hydrodynamics, could model how material would be ejected, heated, vaporized, and redistributed during and after such an impact. What her models showed was both terrifying and beautiful. The collision began with Theia striking Earth's surface at an acute angle. Within the first few seconds, shock waves propagated through both bodies at speeds exceeding the speed of sound in rock. The energy released was beyond comprehension, equivalent to billions of thermonuclear weapons detonating simultaneously. Temperatures at the impact site soared to tens of thousands of degrees, hot enough to vaporize solid rock instantly. Theia was destroyed almost immediately. The smaller body could not survive the encounter. Its rocky mantle was shattered and stripped away. Its iron core, denser and more resilient, penetrated deeper into Earth before being slowed, fragmented, and eventually absorbed into Earth's own core. Within hours of the impact, Theia as a coherent body had ceased to exist, but its material lived on. The impact excavated vast quantities of rock from both Theia and Earth's mantle, hurling them into space at velocities high enough to achieve orbit. The oblique angle of the collision was critical here. Material ejected at the right angles, and velocities did not escape into interplanetary space or fall back to Earth immediately. Instead, it was caught in orbit, forming a disk of superheated debris encircling the wounded planet. Earth itself was transformed. The impact set our planet spinning much faster than it does today, with a day lasting perhaps only 5 or 6 hours. The entire outer portion of the planet was melted, covered in a global ocean of magma hundreds of kilometers deep. Temperatures at the surface exceeded 2,000 degrees Celsius. The atmosphere was replaced by a thick envelope of vaporized rock, a silicate fog so dense that it would have glowed red with its own heat. For a time, Earth wasn't a planet as we would recognize it. It was a seething, molten, hellish world wrapped in rock vapor, orbited by a disk of glowing debris. Nothing could have survived on its surface. The distinction between solid and liquid was meaningless. The entire outer shell of the planet was churning, convecting, radiating heat into space. And in the sky above this inferno, the moon was being born. The disk of debris surrounding Earth was not stable. Gravity pulled at it constantly, and collisions between the trillions of fragments began almost immediately. Within the first few years after the impact, material in the outer portions of the disk, beyond a boundary called the Roche limit, where tidal forces become too weak to prevent gravitational clumping, began to accumulate. Recent simulations by Canup, along with subsequent work by researchers around the world, have refined our understanding of how quickly this process occurred. The initial accumulation was rapid. Within the first few years after the impact, material in the outer portions of the disk, beyond the Roche limit, began to clump together under its own gravity. Within decades, a significant proto-moon had formed, containing perhaps half of the moon's eventual mass. This early body orbited very close to Earth, perhaps only 15,000 to 20,000 miles away, close enough that it would have dominated the sky, appearing many times larger than the moon does today. The environment of the early moon was hellish, still glowing with heat from its formation, bombarded by debris still falling inward from the dissipating disk. It hung in a sky illuminated by the molten surface of the Earth below. The gravitational interaction between Earth and its new satellite caused tremendous tidal forces, generating additional heat within both bodies. The Earth's surface was a magma ocean, the moon's surface was a magma ocean, and the space between them was filled with vaporized rock and debris. The growth then stalled temporarily as the inner disk, closer to Earth, spread outward due to internal friction and viscosity. Over the next few hundred years, additional material migrated beyond the Roche limit, spawning smaller moonlets that spiraled outward and were absorbed by the growing moon. Some models suggest the entire process from impact to a recognizable solid moon took only about 1,000 years. Other researchers have proposed longer timescales, perhaps 10,000 to 100,000 years, depending on the specific conditions of the debris disk. But in geological terms, even the longer estimates are instantaneous. The moon formed in the blink of a cosmic eye. Throughout this process, tidal interactions between Earth and the growing moon began to push the satellite outward. Even in those early days, the same gravitational forces that cause ocean tides today were at work. transferring angular momentum from Earth's rotation to the Moon's orbit, slowing our planet's spin and increasing the Moon's orbital distance. This process has continued for 4.5 billion years, and it continues today. The Moon recedes from Earth by about 3.8 centimeters per year. What emerged from this violent birth was a world unlike any other in the solar system. The Moon had inherited material from both Theia and Earth's mantle, but almost none from their iron cores. This explained one of the great puzzles that had confronted earlier theories. Why is the Moon so much less dense than Earth? The answer was that the iron, the heaviest component of both bodies, had largely remained with Earth. The debris disk consisted primarily of silicate mantle material, rocky and relatively iron-poor. The Moon was also born hot. The energy of the impact and the subsequent accretion had melted its outer layers completely, creating a global ocean of magma that would take millions of years to cool and solidify. And it was dry. The intense heat had vaporized any water or other volatile compounds that might have been present in the original material. By the time the debris cooled enough to coalesce, those volatiles had escaped to space. In one cataclysmic event lasting perhaps a few hours, followed by centuries of gradual accumulation, a new world had been created. Theia was gone, absorbed into both Earth and Moon. But in its death, it had given rise to the satellite that would shape Earth's future in ways that were only beginning to be understood. The giant impact hypothesis, once dismissed as too extreme, had become the leading explanation for the Moon's origin. But as we shall see, the evidence from the Apollo samples would create new puzzles even as it confirmed the basic outline of this violent birth. When the debris from the Great Collision finally coalesced into the Moon, the newborn satellite was not the cold, gray world we see today. It was a seething ball of molten rock, glowing orange and red against the darkness of space. The energy of accretion, as countless fragments crashed together at tremendous velocities, had heated the Moon's outer layers to temperatures exceeding 1,500 degrees Celsius. For millions of years after its birth, the Moon was wrapped in an ocean of fire. This is the lunar magma ocean, one of the most important concepts to emerge from the study of Apollo samples, and a key to understanding not only how the Moon evolved, but how rocky planets in general differentiate into the layered structures we see today. The idea first took shape in 1970, when scientists began analyzing the peculiar rocks brought back by Apollo 11. Among the samples were fragments of anorthosite, a light-colored rock composed almost entirely of the mineral plagioclase. On Earth, anorthosite is relatively rare, found in ancient mountain ranges and in a few layered igneous intrusions. But on the Moon, anorthosite was everywhere in the highlands, the bright, heavily cratered regions that cover most of the lunar surface. Two independent research groups, one led by John Wood, the Smithsonian Astrophysical Observatory, and another by John Smith and colleagues, recognized the significance of this finding almost simultaneously. Plagioclase is a lightweight mineral compared to the iron and magnesium-rich silicates that make up most of a planet's mantle. If the Moon's outer layers had been molten, plagioclase crystals would have floated to the surface like ice on water, while denser minerals sank toward the interior. The Faroan anorthosites, as these lunar highland rocks came to be called, were remarkably pure, consisting of more than 90% plagioclase. This purity was itself evidence of a global-scale melting event. Only if vast quantities of magma had been present, allowing crystals to separate efficiently by density over extended periods, could such pure anorthosite have formed. How deep was this magma ocean? The question has occupied researchers for decades, and the answer has important implications for the Moon's thermal history and internal structure. Early estimates suggested a relatively shallow magma ocean, perhaps 200 to 400 kilometers deep. But more recent studies, incorporating improved experimental data on mineral crystallization and density, have revised these estimates dramatically upward. Some models now suggest that the magma ocean extended to depths of 1,000 kilometers or more, encompassing the entire lunar mantle. A few researchers have even proposed a whole Moon magma ocean, with molten material extending all the way to the center. The most recent thermal models, published in 2020 and later, suggest that a magma ocean approximately 1,000 kilometers deep best explains the available evidence. This model places the inner radius of the molten zone at about 740 kilometers from the Moon's center, with the outer boundary at the surface, a total depth that would have contained the majority of the Moon's silicate volume. Imagine this world in its infancy. The surface glowed with the heat of molten rock, radiating energy into space. There was no solid crust, no craters, no distinction between Highlands and Maria. Just an endless expanse of churning, convecting magma, punctuated perhaps by fountains of vaporized rock, where particularly vigorous convection brought superheated material to the surface. The cooling process that transformed this hellscape into the Moon, we know today, unfolded over tens of millions of years, perhaps as long as 150 to 200 million years according to some estimates. Crystallization began at the bottom of the magma ocean, where pressures were highest and temperatures could be reduced most effectively by heat loss to the lunar interior. The first minerals to solidify were dense, magnesium-rich silicates, olivine and pyroxene. These crystals, heavier than the surrounding melt, sank toward the Moon's center, building up a cumulate pile on the floor of the magma ocean. As crystallization proceeded and the magma ocean gradually shrank, its composition evolved. The removal of early crystallizing minerals left the remaining liquid enriched in elements that did not fit easily into the crystal structures of olivine and pyroxene, elements like calcium, aluminum, potassium, and rare earth metals. Eventually, the magma ocean cooled to temperatures where plagioclase became stable, and here is where the Moon's unique character emerged. Plagioclase, particularly the calcium-rich variety called anorthite, is less dense than silicate melt at the low pressures of the lunar interior. When plagioclase crystals formed, they did not sink like the earlier minerals, they floated. This flotation process created the lunar highlands. Plagioclase crystals rose through the magma ocean and accumulated at the surface, gradually building up a crust of anorthosite that insulated the remaining melt below. The crust grew thicker over time as more plagioclase crystallized and floated upward, eventually reaching thicknesses of 40 to 50 kilometers. But the story does not end there. As the magma ocean approached complete solidification, the last dregs of melt became extraordinarily enriched in elements that had been rejected by all the earlier crystallizing minerals. These incompatible elements, as geochemists call them, concentrated in the residual liquid to remarkable degrees. The final product of this concentration process is known as CREEP, an acronym that stands for potassium, K, rare earth elements, REE, and phosphorus, P. CREEP also contains high concentrations of uranium and thorium, radioactive elements whose decay generates heat. The CREEP layer, representing the ultimate residue of magma ocean crystallization, is estimated to have formed a layer perhaps 2 to 6 kilometers thick, sandwiched between the anorthosite crust above and the dense cumulate mantle below at depths of roughly 30 to 50 kilometers. The chemistry of CREEP is truly remarkable. The incompatible elements are concentrated by factors of hundreds or even thousands compared to typical lunar rocks. Uranium and thorium abundances are so high that CREEP-rich regions generate significantly more internal heat than other parts of the Moon. This radioactive heat likely prolonged volcanic activity in regions underlain by CREEP, explaining why the nearside Maria, which overlie CREEP-rich material, are more extensive than the limited volcanic deposits on the far side. CREEP-rich rocks have been found at several Apollo landing sites, particularly Apollo 12, 14, and 15. They represent samples of this ancient residual layer excavated by later impacts and scattered across the surface. The presence of CREEP has profound implications for lunar thermal evolution because its radioactive elements continue to generate heat to this day. The distribution of CREEP is not uniform across the Moon. It is concentrated in a region called the Procellarum CREEP terrain on the near side, possibly explaining why volcanic activity was more extensive there than on the far side. Some researchers have proposed that the asymmetric distribution of creep may be related to the giant impact itself. If the impact occurred at an oblique angle, as most models suggest, it could have produced an asymmetric debris disk and an asymmetric moon. Alternatively, a later impact, perhaps the one that formed the enormous South Pole Aitken Basin on the far side, might have redistributed material within the moon, concentrating creep on the near side through mechanisms that are still being investigated. The lunar magma ocean hypothesis has been refined substantially since it was first proposed. One of the most significant recent developments is the concept of the slushy magma ocean. Traditional models assumed that the magma ocean was completely liquid, with crystals forming and immediately separating from the melt. But experimental and theoretical work over the past decade suggests a more complex picture. The magma ocean may have contained suspended crystals throughout much of its history, particularly in its later stages. Rather than a clear liquid with crystals sinking or floating, it may have been more like a partially frozen slurry, with crystals of various sizes distributed throughout the convecting fluid. This slushy magma ocean model helps explain some features of lunar rocks that are difficult to account for with simpler models, including certain trace element patterns and the distribution of ages among highland samples. If crystals were suspended rather than immediately separated, the chemical evolution of the remaining liquid would have followed different paths, leaving different fingerprints in the final products. The timescale of magma ocean solidification has also been revised. Early models suggested rapid cooling, perhaps 10 to 20 million years, but recent thermal models that account for the insulating effect of the growing anorthosite crust, along with heat generated by radioactive decay in the residual creep layer, suggest much longer timescales. The magma ocean may have taken 150 to 200 million years to solidify completely, with the last pockets of creep-rich melt persisting until approximately 4.3 billion years ago. Why does all of this matter? Because the lunar magma ocean has preserved a record of planetary differentiation that has been lost on Earth. Our planet also experienced global-scale melting early in its history, likely multiple times during the giant impact and the preceding period of accretion. Earth, too, developed a layered structure with a dense iron core, a silicate mantle, and a lighter crust. But Earth's subsequent evolution, driven by plate tectonics, volcanic resurfacing, and chemical recycling through the atmosphere and oceans, has erased virtually all direct evidence of that early magma ocean. The Moon, in contrast, has been geologically dead for billions of years. Its crust, formed during the final stages of magma ocean crystallization, has survived largely intact, preserved by the absence of the processes that continually reshape Earth's surface. When we study the lunar highlands, we are looking at rocks that crystallized from a magma ocean more than 4.4 billion years ago. They are windows into a time when the inner solar system was still forming, when rocky planets were molten balls of fire rather than the solid worlds we know today. The Pharaohan anorthosites, the creep basalts, the cumulate mantle rocks exposed by giant impacts, all of these lunar samples tell us about processes that must have occurred on Earth as well, but for which we have no terrestrial record. The Moon is a laboratory for understanding planetary differentiation, a preserved example of how rocky worlds organize themselves into the layered structures that make possible everything from magnetic fields to volcanic eruptions to the movement of tectonic plates. In this sense, the Moon is not just Earth's companion, it is Earth's memory, holding secrets about our own planet's earliest days that we could never recover from Earth itself. The giant impact hypothesis seemed to explain so much: the Moon's lack of iron, its extreme dryness, the energy required to create a global magma ocean, and the high angular momentum of the Earth-Moon system. By the 1984 Lunar Origins Conference in Kona, Hawaii, the hypothesis had achieved something close to scientific consensus. The major competing theories had been weighed against the Apollo evidence and found wanting. The giant impact was the last theory standing. But science never stops questioning, and as analytical techniques improved through the 1990s and 2000s, a troubling problem emerged. The giant impact model, in its original form, made predictions that did not quite match the data. The closer scientists looked at the isotopic composition of lunar rocks, the more difficult it became to explain what they found. The problem centered on oxygen isotopes, those atomic fingerprints that scientists had used since the Apollo era to identify the origins of solar system materials. Oxygen has 3 stable isotopes: oxygen-16, oxygen-17, and oxygen-18. The ratios between these isotopes vary throughout the solar system, reflecting the different conditions under which various bodies formed. Mars has a distinctive oxygen isotope ratio. So does Vesta, the large asteroid sampled by meteorites that have fallen to Earth. So do the various classes of chondrites, primitive meteorites that represent the original building blocks of the planets. These differences are not subtle. Using high-precision mass spectrometry, scientists can distinguish the oxygen isotope signatures of different planetary bodies with extraordinary accuracy. The isotopic composition of oxygen serves as a kind of blood type for rocks, allowing researchers to identify where materials originated, even when they are found far from their source. When scientists measured the oxygen isotopes in lunar samples with ever-increasing precision, they discovered something remarkable. Earth and Moon had virtually identical oxygen isotope ratios, not similar, not close, identical within the limits of measurement. Later studies pushed this comparison to the level of a few parts per million, and still the two bodies matched. To put this in perspective, consider how different other solar system bodies are. Martian meteorites have oxygen isotope ratios that differ from Earth's by several parts per thousand, a difference that is immediately obvious with modern instruments. The Vesta asteroid, sampled by HED meteorites, differs by even more. Even bodies that formed relatively close to Earth in the solar nebula have distinct isotopic signatures that allow scientists to identify their origins with confidence. Yet the Moon matches Earth exactly. If you were to analyze a lunar rock and an Earth rock without knowing their origins, you could not tell them apart based on oxygen isotopes alone. They are, in this fundamental chemical sense, identical twins. This was not what the standard giant impact model predicted. In the simulations developed by Robin Canup and others, the Moon formed primarily from the debris of Theia, the impactor. Some material from Earth's mantle was also ejected, but the impactor contributed the majority of the Moon-forming disk. If Theia had formed elsewhere in the solar system, even somewhere relatively close to Earth's orbit, it should have had a different oxygen isotope signature. That signature should have been imprinted on the Moon, but the Moon and Earth are isotopic twins. The puzzle deepened when scientists examined other isotope systems. Titanium isotopes, which vary significantly among solar system bodies, also proved virtually identical between Earth and Moon. Tungsten isotopes, products of radioactive decay that can constrain the timing of planetary differentiation, showed the same pattern. Chromium, silicon, and other elements all told the same story. Whatever process created the Moon, it had produced a body whose isotopic composition was indistinguishable from Earth's mantle. This became known as the isotope crisis, and for a time it threatened to undermine the giant impact hypothesis entirely. Several solutions were proposed, each with strengths and weaknesses. One possibility was that Theia happened to have the same isotopic composition as Earth. If Theia formed very close to Earth in the solar nebula, perhaps at the same radial distance from the Sun, it might have incorporated the same mix of oxygen isotopes. Some dynamical simulations supported this idea, suggesting that impactors were more likely to have similar compositions to their targets than previously thought. But the probability of such a precise match, extending across multiple isotope systems, seemed low. A second possibility was vigorous mixing. Perhaps the giant impact was so energetic that it thoroughly homogenized the debris from both Theia and Earth before the Moon formed. Kaveh Pelevin and David Stevenson at Caltech proposed in 2007 that in the aftermath of the impact, Earth and the proto-lunar disk could have been connected by a common silicate vapor atmosphere. Convective mixing within this atmosphere might have equilibrated the isotopic compositions of the two reservoirs over a period of roughly 100 years. This solution was promising, but required specific conditions. The proto-lunar disk would need to persist long enough for mixing to occur, and the temperatures would need to remain high enough to maintain the vapor connection. Whether these conditions could actually be achieved remained uncertain. A more radical solution emerged in 2012 when two papers published simultaneously in Science proposed entirely new impact scenarios. Mattia Chuk and Sarah Stewart suggested that the giant impact struck a rapidly spinning proto-Earth. In their model, the young Earth was already rotating extremely fast, with a day lasting only about 2 to 3 hours before the impact occurred. A smaller, faster impactor could then eject material primarily from Earth's mantle, rather than from the impactor itself. The Moon would be made almost entirely of terrestrial material, explaining the isotopic similarity. This scenario required a mechanism to slow Earth's rotation after the Moon formed, since our current 24-hour day is far longer than the 2-hour day required by the model. Chuck and Stewart proposed that a gravitational resonance with the Sun could have transferred angular momentum from the Earth-Moon system to Earth's orbit around the Sun, gradually slowing our planet's rotation over millions of years. Robin Canup, in the companion paper, explored a different possibility. What if the impactor and proto-Earth were roughly the same size? In a collision between two nearly equal bodies, both would be largely destroyed and mixed. The resulting debris disk would contain material from both objects in roughly equal proportions, and even if their original compositions differed, the final Moon would represent an average of the two. Both of these scenarios could potentially explain the isotopic similarity, but they required conditions different from the original canonical impact, either a rapidly spinning target or two similarly sized colliders. Then, in 2017 and 2018, a new idea emerged that would reframe the entire discussion. Simon Locke, a graduate student at Harvard working with Sarah Stewart, now at UC Davis, proposed that high-energy giant impacts could create a previously unrecognized type of astronomical structure. They called it a synestia. A synestia is not a planet. It is not a planet with a disk. It is something entirely different, a donut-shaped cloud of vaporized rock, spinning so rapidly that its outer regions cannot be gravitationally bound in the normal sense. The structure extends far beyond where a conventional planetary surface would be, enveloping a huge volume of space in superheated silicate vapor. Locke and Stewart showed that when two planet-sized bodies collide with sufficient energy and angular momentum, the result exceeds what they called the corrotation limit, the maximum thermal energy and angular momentum a body can have while still rotating as a coherent unit. Beyond this limit, a synestia forms. In their model of lunar formation, the giant impact created a terrestrial synestia, a vast, glowing, rapidly spinning structure that temporarily replaced both Earth and the debris disk. The Moon then formed within this structure, not from a disk orbiting outside a defined planetary surface, but from condensing droplets within the synestia itself. Because both the Moon and the eventual Earth condensed from the same well-mixed cloud of vaporized rock, they naturally inherited the same isotopic composition. The isotope crisis dissolves in this view because the very distinction between impactor material and target material became meaningless within the homogenized synestia. The synestia model can also explain the Moon's depletion in volatile elements. Within the high-pressure, high-temperature environment of the synestia, the growing Moon would have been surrounded by rock vapor at temperatures of 2,200 to 3,300 degrees Celsius. Any volatile compounds would have been unable to condense onto the lunar surface under these conditions. More recently, in late 2024 and 2025, new research has continued to refine our understanding. Studies from the University of Göttingen and elsewhere have suggested that the Moon formed primarily from material derived from Earth's mantle, supporting the high-energy impact models over the canonical scenario. High-precision measurements of isotope ratios continue to push the boundaries of what we know, with some studies suggesting subtle differences between Earth and Moon at the parts per million level that might preserve faint traces of Thea's original composition. The current scientific consensus, to the extent that one exists, favors some version of the giant impact that can explain the isotopic similarities. Whether this means a fast-spinning Earth, two similarly sized colliders, or formation within a synestia remains actively debated. The synestia model has gained considerable traction because it elegantly solves multiple problems at once, but it has not yet achieved universal acceptance. What is clear is that the simple picture of a Mars-sized Theia striking a slowly rotating Earth and ejecting debris that formed the Moon has given way to more complex scenarios. The isotope crisis forced scientists to think harder about the physics of giant impacts, and the result has been a richer, more nuanced understanding of how the Earth-Moon system came to be. The Moon's isotopic fingerprint, once a puzzle, has become a powerful constraint that guides our models toward the truth. Whatever happened 4.5 billion years ago, it must have produced two bodies that are chemical twins. That simple fact rules out many scenarios and points toward impacts of extraordinary violence and thorough mixing. We are still refining our understanding. Future lunar sample return missions, particularly from the far side and polar regions, may provide new isotopic data that further constrain the models. But the basic insight remains: the Moon is made of the same stuff as Earth because both emerged from the same cosmic catastrophe. After the fires of the magma ocean cooled and the anorthosite crust solidified, the Moon was not left in peace. The early solar system was a violent place, littered with the debris of planet formation, and the young Moon bore the full brunt of this cosmic chaos. The scars of that bombardment remain visible today, etched into the lunar surface in the form of craters, basins, and the dark lava plains that ancient astronomers mistook for seas. The story of lunar bombardment is also the story of early Earth, for our planet would have experienced the same hail of impacting bodies. But Earth has erased its ancient craters through geological activity. The Moon preserves them, a witness to a time when impacts that could sterilize a planet were routine events. Among the most significant concepts to emerge from the study of lunar samples was the hypothesis of the late heavy bombardment. This idea, born from the analysis of Apollo rocks, proposed that the inner solar system experienced a dramatic spike in impact rates approximately 3.9 to 4.0 billion years ago, hundreds of millions of years after the planets had largely finished forming. The evidence came from radiometric dating of impact melt rocks, samples created when asteroids or comets struck the lunar surface with enough energy to melt the target rock. When Apollo astronauts collected samples from the regions around major impact basins, scientists in Earth-bound laboratories dated these samples using isotopic techniques, particularly the decay of potassium-40 to argon-40. What they found was unexpected. The impact melt ages clustered remarkably tightly around 3.9 billion years ago, give or take a few hundred million years. The Apollo 15, 16, and 17 landing sites had been chosen specifically because of their proximity to three enormous impact basins, Imbrium, Nectaris, and Serenitatis. If the melt rocks at these sites dated to similar ages, it suggested that these basins, three of the largest scars on the near side, had formed in a relatively narrow window of time. Fuad Terra and colleagues at Caltech first proposed in 1974 that this clustering of ages indicated a lunar cataclysm, a period of intense bombardment that created most of the Moon's large basins in a geologically brief interval. The idea was controversial, but compelling. If confirmed, it meant that the inner solar system had experienced a dramatic surge in violence long after the main phase of planet formation had ended. Various mechanisms were proposed to explain such a bombardment spike. The most influential is the NICE model, named after the French city where it was developed. This model suggests that the giant planets, particularly Jupiter, Saturn, Uranus, and Neptune, underwent a period of orbital migration and gravitational instability several hundred million years after the solar system formed. During this instability, the asteroid belt and the Kuiper belt were severely disrupted, sending showers of impactors into the inner solar system. But the late heavy bombardment hypothesis has always been controversial, and in recent years, significant doubts have emerged. One major criticism is that the Apollo samples might not represent impacts from different basins at all. The Imbrium Basin, the largest and youngest of the major nearside basins, would have distributed ejecta across all the Apollo landing sites. The cluster of 3.9 billion-year-old melt rocks might simply reflect sampling of Imbrium debris rather than multiple basin-forming events. Furthermore, as analytical techniques have improved, evidence for impacts older than 4 billion years has begun to emerge. Some researchers now favor a more gradual decline in bombardment rates rather than a sudden spike, with impacts decreasing steadily from the end of planet formation through to the present day. The debate continues, and a decisive resolution may require samples from lunar basins that have not been contaminated by Imbrium ejecta, perhaps from the South Pole Aitken Basin on the lunar far side, the oldest and largest impact structure preserved on the Moon. Whatever the timing, the bombardment was devastating. The lunar surface records impacts at every scale, from microscopic pits left by interplanetary dust to basins hundreds of kilometers across. One of the most spectacular examples is Mare Orientale, visible at the extreme western edge of the lunar nearside. This multi-ring basin, approximately 930 kilometers in diameter, is the youngest of the large lunar impact structures formed about 3.8 billion years ago. Unlike older basins that have been flooded by volcanic lava, Orientale is only partially filled, leaving its internal structure exposed for study. The Lunar Reconnaissance Orbiter has provided stunning images of Orientale, revealing the concentric rings that mark the basin's structure. 3 major ring systems are visible: the inner Rook Mountains, the outer Rook Mountains, and the outermost Cordillera Mountains. These rings formed as the lunar crust collapsed inward after the initial impact cavity was excavated. Recent simulations suggest that the Orientale impact was caused by an asteroid approximately 64 kilometers in diameter, striking at about 15 kilometers per second. The collision excavated a transient crater roughly 320 kilometers across and as deep as 180 kilometers, temporarily exposing material from deep within the lunar mantle. But this cavity was unstable. Within hours, gravitational collapse caused the floor to rebound and the walls to slump inward, creating the complex ring structure we see today. The study of Orientale has been crucial for understanding how multi-ring basins form on the Moon, Mercury, and other cratered worlds. Because Orientale is relatively well preserved, it serves as a template for interpreting older, more degraded basins elsewhere in the solar system. The Lunar Reconnaissance Orbiter has mapped the entire lunar surface at resolution sufficient to reveal individual boulders. This global survey has cataloged craters of all sizes and ages, providing an unprecedented view of the Moon's impact history. Among the features revealed are some remarkably young craters, reminders that bombardment continues to the present day, albeit at much lower rates than in the ancient past. Consider the Aristarchus Plateau, a fascinating region in the northwest portion of the lunar nearside. Here, a mysterious sinuous rill, a channel carved by flowing lava billions of years ago, cuts across the landscape. 2 immense craters punctuate the plateau. One of these, Aristarchus crater itself, was created by an impact just 450 million years ago, making it one of the youngest large craters on the Moon. At 40 kilometers in diameter, Aristarchus is bright enough to be visible to the naked eye from Earth, a splash of brilliant white against the darker mare basalt surrounding it. The impact that created it was powerful enough to excavate material from deep beneath the surface, exposing volcanic glass deposits that are the legacy of ancient eruptions. Along the crater walls, blocks of rock from the lunar crust stand fractured and exposed, samples waiting for future explorers. The rays of bright ejecta extend for hundreds of kilometers in all directions, testament to the violence of the event that occurred during the Ordovician period on Earth, when life was confined to the oceans and the continents were barren rock. Even younger is Tycho crater, formed by an impact approximately 100 million years ago when dinosaurs still roamed the Earth. At 85 kilometers across, Tycho is a prominent feature on the lunar nearside, notable for its bright ray system that extends across much of the visible hemisphere. These rays, composed of finely pulverized rock ejected during the impact, can be traced for distances exceeding 2,500 kilometers, making Tycho one of the most distinctive features visible from Earth with the naked eye during a full moon. Images from the Lunar Reconnaissance Orbiter have revealed extraordinary details within Tycho. The central peak, rising approximately 2 kilometers above the crater floor, is material that rebounded from the deep lunar interior during the moments after impact. The crater walls display complex terracing, the result of gravitational collapse and slumping in the hours and days following the impact. Sitting on the summit of this central peak is a mysterious boulder, roughly 120 meters wide, somehow perched at the highest point. Around this boulder and on it, scientists have detected evidence of rock that was melted in the heat of the impact itself, indicating temperatures that exceeded 1,000 degrees Celsius. How did this boulder come to rest at the top of the central peak? One theory suggests it rode up on the rebounding floor material during crater formation, carried along like a surfer on a wave of molten rock. Another proposes it was ejected from the impact zone and happened to land at this location. A third possibility is that it was never moved at all, that it was part of the lunar crust that survived the impact relatively intact, while the material around it was excavated and redistributed. Whatever the explanation, it stands as a testament to the extraordinary dynamics of large impact events, dynamics that can only be fully understood through further exploration. The lunar crater record tells us about more than just the moon. It provides our best window into the bombardment history of the early Earth. Earth is close enough to the moon that both bodies would have experienced similar impact fluxes. When the moon was being scarred by the late heavy bombardment or by the declining tail of bombardment after planet formation, Earth was being hit just as hard. Many of the impactors would have been large enough to vaporize oceans, melt the crust, or sterilize the surface. The oldest evidence for life on Earth dates to approximately 3.5 to 3.8 billion years ago, not long after the proposed period of intense bombardment. Some researchers have suggested that the bombardment may have actually delayed the emergence of life by repeatedly sterilizing the surface. Others have proposed that impacts could have delivered organic molecules or created environments favorable for life's origin. In 2014, scientists reported evidence for the largest known terrestrial impact near the Barberton Greenstone Belt in South Africa. This impact, estimated to have occurred about 3.26 billion years ago, was caused by an impactor perhaps 37 to 58 kilometers across, far larger than the asteroid that killed the dinosaurs. The crater itself, if it still exists, has not been found. But the spherule beds, layers of tiny glass beads formed when vaporized rock condensed and fell back to Earth, preserve the record of this ancient catastrophe. The moon's craters are a cosmic Rosetta Stone that allows us to decode the bombardment history of all the inner planets. By counting craters on different surfaces and correlating them with the radiometric ages of Apollo samples, scientists have developed chronologies that can be applied to Mars, Mercury, and even the moons of the outer solar system. The current understanding favors a more nuanced view than either a pure late heavy bombardment or a simple gradual decline. Multiple populations of impactors may have contributed to the cratering record at different times, leftover planetesimals from the primary accretion period, asteroids destabilized by the migration of the giant planets, and comets scattered inward from the outer solar system. Whatever the precise history, the message of the craters is clear. The young solar system was a dangerous place, and the moon has preserved the scars to prove it. In studying those scars, we learn about the forces that shaped not only the moon, but Earth and all the worlds of the inner solar system. Every crater is a record, every basin is a chapter, and together they tell a story of violence that eventually gave way to the relative calm in which life could emerge, evolve, and eventually send representatives to the moon to collect the very rocks that would reveal this history. For decades after Apollo, there was one thing that every textbook agreed upon. The moon was bone dry. Not a little dry like a desert, but utterly, completely, absolutely desiccated. No water had ever existed on its surface, and none was locked within its interior. This dryness was not merely an observation, but a prediction, a logical consequence of the giant impact hypothesis. The violence of the collision The extreme temperatures of the debris disk, the subsequent magma ocean that covered the newborn moon, all of these processes should have driven off any water and other volatile compounds, evaporating them into space where they were lost forever. The early Apollo sample analyses seem to confirm this expectation. When scientists examined the lunar rocks with the best instruments available in the 1970s, they found no detectable water. The moon, it appeared, was as dry as promised, but science is a process of constant revision, of measuring with greater precision, of asking old questions with new tools. And as the decades passed, the story of lunar water began to change in ways that no one had anticipated. The first hints came not from the Apollo samples themselves, but from orbit. In 1998, NASA's Lunar Prospector spacecraft began an ambitious mission to map the entire lunar surface using a suite of scientific instruments. Among these was a neutron spectrometer, a device designed to detect hydrogen by measuring how neutrons from cosmic ray impacts interact with surface materials. Hydrogen, the scientists knew, has a distinctive effect on neutrons. When cosmic rays strike the lunar surface, they generate fast-moving neutrons that scatter through the soil. If hydrogen is present, it absorbs energy from these neutrons, slowing them down. By measuring the population of slow or epithermal neutrons coming from the lunar surface, the spectrometer could map hydrogen distribution. What Lunar Prospector found was startling. Around both the north and south poles of the moon, the neutron flux dropped significantly, indicating elevated hydrogen concentrations. If this hydrogen was in the form of water ice, it could represent hundreds of millions of tons of frozen water hiding in the perpetual darkness of polar craters. The polar regions are unique environments on the moon. Because the moon's axis is tilted only about 1.5 degrees relative to the plane of the solar system, the sun's rays strike the polar regions at extremely shallow angles. At the bottoms of some craters near the poles, sunlight has not shone for billions of years. These permanently shadowed regions are among the coldest places in the solar system, with temperatures dropping to -240 degrees Celsius, colder even than the surface of Pluto. At such temperatures, water ice is stable. Any water molecule that drifts into one of these cosmic cold traps will freeze instantly and remain frozen essentially forever, protected from the solar radiation that would otherwise break it apart. But the Lunar Prospector data, while suggestive, was not definitive. The hydrogen signal could be interpreted as water ice, but it could also be explained by implanted hydrogen from the solar wind, protons from the sun that had been embedded in the lunar soil over billions of years. To truly confirm the presence of water, scientists needed to get closer. In 2009, NASA launched a bold mission designed to do exactly that. The Lunar Crater Observation and Sensing Satellite, or LCROSS, had a simple but dramatic objective: crash a rocket into a permanently shadowed crater and analyze the debris cloud that resulted. The target was Cabeus Crater, a 98-kilometer-wide depression near the lunar South Pole. Cabeus had been selected because temperature measurements indicated that its permanently shadowed floor was among the coldest regions on the moon, making it an ideal cold trap for volatiles. On October 9, 2009, the LCROSS mission reached its climax. The spent Centaur upper stage of the rocket that had launched LCROSS separated and plunged toward Cabeus at nearly 9,000 kilometers per hour. When it struck, it excavated a crater roughly 20 meters across and ejected approximately 350 metric tons of lunar material. Following just 4 minutes behind, the LCROSS shepherding spacecraft flew through the rising debris plume, its instruments recording everything they could before the spacecraft itself crashed into the lunar surface. Above, the Lunar Reconnaissance Orbiter also trained its instruments on the impact site, gathering additional data. The results exceeded expectations. In the debris cloud rising from Cabeus Crater, scientists detected clear spectral signatures of water, both as ice crystals and as vapor. Analysis indicated that approximately 5.6% of the material in the crater floor consisted of water ice, a concentration higher than some desert soils on Earth. But water was not the only thing hiding in the eternal darkness of Cabeus. The debris cloud also contained carbon monoxide, ammonia, methane, mercury, magnesium, calcium, and sodium. The permanently shadowed craters of the moon, it turns out, are not merely water reservoirs. They are cosmic refrigerators that have been collecting volatile compounds delivered by comets and asteroids for billions of years. Meanwhile, another spacecraft was revolutionizing our understanding of water distribution across the entire lunar surface. India's Chandrayaan-1 mission, launched in 2008, carried an instrument called the Moon Mineralogy Mapper, or M3, built by NASA. In 2009, the M3 team announced a discovery that stunned the lunar science community. Water, or more precisely, hydroxyl, was present not just at the poles but across large portions of the lunar surface. The spectral signatures appeared strongest at high latitudes and in the morning hours, suggesting a dynamic process in which water molecules migrate across the lunar surface, accumulating in cooler regions during the lunar night and being released as temperatures rise. The hydroxyl detected by M3 was not ice, but rather molecules chemically bound within the surface minerals. It was present in very low concentrations, perhaps a few hundred parts per million, but it was there, distributed widely across a world that was supposed to be utterly dry. Where was this surface water coming from? One source appears to be the solar wind itself. The constant stream of protons from the sun strikes the lunar surface and can chemically react with oxygen atoms in the minerals, generating hydroxyl and water molecules. This process essentially creates water in place, forming it directly within the lunar soil. But the greatest surprise was yet to come, and it emerged from a source that had been collecting dust in laboratories for nearly 40 years. The Apollo samples themselves. In 2008, Alberto Sal at Brown University and his colleagues published research that forced a fundamental reassessment of what we thought we knew. Using advanced analytical techniques that had not existed during the Apollo era, they examined tiny glass beads within lunar volcanic samples. These beads, formed when lava erupted and cooled rapidly billions of years ago, were time capsules preserving the composition of ancient lunar magmas. To their amazement, the researchers found water not on the surface of the beads, but trapped within them. The water concentrations were low by terrestrial standards, ranging from about 10 to 50 parts per million in the measured samples, but they were unmistakably present. In 2011, follow-up studies of melt inclusions, tiny pockets of magma trapped within crystals, revealed even higher water contents, up to 100 parts per million, comparable to some volcanic rocks on Earth. The implications were profound. If water was present in the magmas that erupted on the ancient moon, then water must have been present in the lunar interior from which those magmas came. The moon was not dry on the inside, as the giant impact hypothesis had predicted. It contained water that had somehow survived the catastrophic violence of its birth. How much water are we talking about? Estimates have varied as researchers have studied more samples and more locations, but some calculations suggest that the lunar interior could contain enough water to cover the entire surface in a layer 1 meter deep if it could somehow be extracted. The polar ice deposits alone could contain 600 billion kilograms of frozen water, enough to fill hundreds of thousands of Olympic swimming pools. For future lunar explorers, this water is far more than a scientific curiosity. It represents a resource that could make long-term human presence on the moon feasible. Water can be split into hydrogen and oxygen by electrolysis, providing breathable air and rocket fuel. It can sustain plants in lunar greenhouses. It can shield habitats from radiation. Finding water on the moon transforms the economics of lunar exploration from an exercise in hauling everything from Earth to a prospect of living off the land. But where did this water come from in the first place, given the extreme conditions of lunar formation? Several hypotheses compete for acceptance. Some of the surface water, particularly the hydroxyl detected by Chandrayaan-1, clearly comes from the solar wind. The polar ice deposits may have been delivered primarily by comets, which are essentially dirty snowballs that have been striking the inner solar system for billions of years. When a water-rich comet impacts the moon, most of its volatiles are vaporized and lost, but some fraction migrates across the surface, before freezing out in the polar cold traps. The water, locked within volcanic glass beads in the lunar interior, is harder to explain. One possibility is that water was incorporated into the moon-forming debris disk from comets that struck during the period of lunar accretion. Another is that not all water was lost during the giant impact, that some fraction survived the extreme temperatures by being chemically bound within minerals that later became part of the moon. A third possibility involves late delivery, water-rich asteroids and comets that impacted the moon after it had largely solidified, mixing their volatiles into the lunar interior through impact-induced melting. The presence of water on the moon does not invalidate the giant impact hypothesis, but it does require that hypothesis to be more nuanced than originally conceived. The formation of the moon was violent, but perhaps not quite violent enough to eliminate all traces of water. Or the water was delivered later, after the fires had cooled. Either way, the textbooks have been rewritten. The moon that Apollo astronauts walked upon, that utterly dry world preserved in the collective scientific memory of the late 20th century, has given way to a more complex and more interesting satellite. There is water on the moon, in the polar shadows and in the ancient volcanic glass and perhaps deep in the interior. And that water may help humanity return to the lunar surface to stay. We have spent much of our time exploring how the moon came to be, tracing the violent collision that created it and the geological processes that shaped it. But there is another side to this story, one that touches directly on why we exist at all. The moon is not merely a companion in the sky. It has been a partner in the development of Earth, influencing our planet in ways so fundamental that without it, the story of life might have unfolded very differently, or perhaps not at all. To understand the moon's gifts to Earth, we must journey back to those earliest days after the giant impact, when the newly formed moon hung so close to our planet that it would have filled the sky. In the immediate aftermath of the collision that created the Earth-Moon system, the moon orbited at a distance of perhaps 20,000 to 25,000 kilometers from Earth, roughly 1/16 of its current distance. At that range, the moon would have appeared not as a modest disk, but as a dominating presence in the sky, perhaps 15 to 20 times its current apparent size. Rising over the horizon, it would have been a vast glowing orb, its surface still red with the heat of formation, its gravitational grip on Earth far stronger than it is today. That gravitational grip manifested most dramatically as tides. Today, the moon's gravity creates gentle rises in the ocean level, typically measured in meters. We notice the tides at coastal regions, where the water advances and retreats twice daily, exposing tide pools and shifting the boundaries between land and sea. These modern tides are a pale shadow of what once existed. When the moon was 10 times closer, its tidal force was 1,000 times stronger. The mathematics of gravity dictate this relationship. Tidal force varies with the inverse cube of distance, so halving the distance increases the force 8-fold, and reducing the distance to 1/10 multiplies the force by 1,000. In those early times, the tides on Earth were not measured in meters, but in hundreds of meters. Massive bulges of water, perhaps reaching heights of several hundred feet, swept around the planet twice with each rotation. The Earth spun much faster then, completing a rotation in as little as 5 or 6 hours. So these mountain ranges of water circled the globe in a relentless cycle, faster than any tsunami, pounding against whatever coastlines existed. The effects were devastating and transformative. Continents, if they existed in any recognizable form, were scoured by walls of water traveling at hundreds of kilometers per hour. Shorelines were zones of constant violent erosion. The ocean floors were stirred and churned. Nothing was stable along the margins of land and sea. Yet this chaos may have been essential for the origin of life. Consider what those ancient tides would have accomplished. With each cycle, they would have torn minerals and nutrients from the land and mixed them into the oceans. Iron, phosphorus, sulfur, nitrogen compounds, and all the other elements that life requires were transported from exposed rocks into the primal seas. The oceans became a rich, concentrated broth of chemicals, what scientists sometimes call the primordial soup. The Bay of Fundy in Canada offers a glimpse into this ancient world in miniature. With tidal ranges reaching 50 feet, it has the largest tides on the modern Earth. Twice each day, billions of tons of water rush into the narrow bay, creating tidal bores that can travel at 15 kilometers per hour. This daily churning shapes the landscape, erodes cliffs, and mixes fresh sediment into the waters. Scale this up by a factor of 10 or 20, speed it up by a factor of 4, and imagine it happening on a global scale. That was the Earth of 4 billion years ago, a world where the moon's gravity stirred the oceans into a chemical reactor capable of concentrating and mixing the ingredients of life. Some researchers have proposed that tidal pools, alternately flooded and exposed, heated and cooled, may have been especially important for prebiotic chemistry. In these dynamic environments, organic molecules could have concentrated as water evaporated, then been diluted and mixed as the tide returned. The rhythmic cycling between wet and dry, hot and cold, dilute and concentrated, might have driven chemical reactions that would otherwise not occur. We cannot prove that the moon was necessary for life's origin. Other energy sources, such as hydrothermal vents or lightning, may have been equally important or more so. But the moon's enormous tides certainly created conditions that were, at minimum, highly favorable for the chemistry that preceded biology. As the eons passed, the tides began to change Earth in another way. The friction of all that moving water, dragging against the ocean floors and continental margins, acted as a brake on Earth's rotation. Think of it this way. The moon's gravity creates tidal bulges in the ocean that tend to align with the Earth-Moon line. But because Earth rotates faster than the moon orbits, friction drags these bulges slightly ahead of that alignment. The gravitational interaction between the moon and these offset bulges creates a torque that gradually slows Earth's spin. The energy lost from Earth's rotation does not disappear. It is transferred to the moon, pushing it into a higher orbit. As Earth slows down, the moon moves farther away. This is happening even today. Laser ranging experiments show that the moon recedes from Earth by about 3.8 centimeters per year, while the length of the Earth's day increases by about 2.3 milliseconds per century. Over 4 billion years, this process has profoundly transformed both bodies. Earth's day has lengthened from those frantic 5 or 6 hours to our current leisurely 24 hours. The moon has retreated from its initially close embrace to its present distance of 380,400 kilometers. The tides have weakened from their ancient fury to the gentle rhythms we know today. But the moon's influence on Earth extends far beyond the tides. Perhaps its most important role, at least for the evolution of complex life, has been to stabilize Earth's axial tilt. Earth's axis is currently tilted at about 23.5 degrees relative to the plane of its orbit around the Sun. This tilt is responsible for our seasons. When the northern hemisphere tilts toward the Sun, it is summer there and winter in the southern hemisphere. 6 months later, the situation reverses. The amount of tilt matters enormously for climate. A larger tilt would mean more extreme seasons, hotter summers, colder winters, greater temperature swings between the tropics and the poles. A smaller tilt would reduce seasonal variation, but might affect the distribution of heat around the planet in complex ways. What keeps Earth's tilt stable? The moon. Without the moon's gravitational influence, Earth's axial tilt would be subject to chaotic variations driven by gravitational perturbations from Jupiter, Venus, and other planets. Computer simulations of a moonless Earth show that its tilt could wander anywhere from nearly 0 degrees to more than 80 degrees over timescales of millions of years. Imagine an Earth whose axis tilts over by 60 or 70 degrees. The poles would experience months of continuous blazing sunlight, followed by months of total darkness. Temperatures at high latitudes would swing from searing heat to extreme cold. The tropics, now relatively constant in temperature throughout the year, would experience wild variations as their orientation to the sun changed drastically. Such an Earth might still support life, but it would be a very different kind of life, adapted to conditions far more extreme than those that have shaped evolution on our actual planet. Complex ecosystems requiring stable climates might never develop. The gradual, Cumulative processes that led from simple bacteria to plants, animals, and eventually humans might be interrupted again and again by climate catastrophes. Mars provides a cautionary example. Mars has two tiny moons, Phobos and Deimos, but neither is massive enough to stabilize the planet's tilt. Over millions of years, Mars's axial tilt has varied from nearly 0 to more than 60 degrees. These swings may have contributed to the dramatic climate changes that have made Mars the cold, dry desert it is today, so different from the warmer, wetter world it appears to have been in its distant past. Our moon keeps Earth's tilt constrained within a narrow range, varying only between about 22.1 and 24.5 degrees over 41,000-year cycles. This stability has persisted for billions of years, providing a consistent platform for the evolution of life. The moon's ongoing recession will eventually reduce its stabilizing influence. In the very distant future, perhaps a billion years or more from now, the moon may be too far away to prevent chaotic tilting. But by that time, the increasing brightness of the aging sun will have made Earth uninhabitable anyway. For now, and for all of recorded geological and biological history, the moon has been Earth's partner in maintaining a hospitable world. It stirred the primordial oceans with ancient tides. It slowed Earth's rotation from a spinning top to a more gentle rhythm. It stabilized Earth's axis, ensuring consistent seasons and gradual climate change rather than chaotic swings. We owe the moon more than we can easily measure. It is not just a light in the night sky, but a cosmic guardian that has shaped the very conditions for our existence. The Apollo program ended in 1972 when Eugene Cernan stepped back into the lunar module of Apollo 17 and left his footprints as the last human tracks on the moon. But the science that Apollo made possible did not end with that final mission. In the half-century since, robotic spacecraft, ground-based observations, and continued analysis of Apollo samples have steadily expanded our understanding of the Earth-Moon system. The legacy of Apollo is not a closed book, but an ongoing story that grows richer with each passing year. One of the most remarkable aspects of this continuing legacy is an experiment that Apollo astronauts placed on the lunar surface and that scientists on Earth continue to use to this day: the Lunar Laser Ranging Retroreflectors. On July 21, 1969, Buzz Aldrin deployed a panel of 100 corner-cube retroreflectors on the surface of the Sea of Tranquility. These simple but elegant devices, each about the size of a thimble, are designed to reflect light directly back toward its source. Point a laser at them from Earth, and the beam bounces straight back. The experiment worked almost immediately. On August 1, 1969, researchers at Lick Observatory in California fired a powerful ruby laser at the Apollo 11 retroreflector and detected the return signal. The round-trip time was approximately 2.5 seconds, allowing them to calculate the Earth-Moon distance with centimeter accuracy, a precision that had never before been achieved. Two more retroreflector arrays were deployed by Apollo 14 and Apollo 15, and the Soviet Union contributed 2 additional reflectors carried by the Lunokhod robotic rovers. For more than 50 years, observatories around the world have been firing laser pulses at these reflectors and timing the returns. The technical challenges are immense. The laser beam spreads out as it travels, so by the time it reaches the moon, it illuminates an area several kilometers across. Only a tiny fraction of the photons actually hit the reflector. On the return trip, the reflected beam spreads out again. Out of approximately 100 quadrillion photons fired toward the moon in a typical pulse, perhaps 1 to 5 photons make it back to the detector. Yet, modern equipment can identify these precious few returning photons and measure their arrival time to within picoseconds. The McDonald Observatory in Texas became the premier lunar laser ranging station during the 1970s and 1980s, producing thousands of high-precision measurements. Today, the Apache Point Observatory Lunar Laser Ranging Operation, or Apollo in New Mexico, achieves millimeter-level precision, measuring the Earth-Moon distance with an accuracy equivalent to determining the distance between Los Angeles and New York to within the width of a human hair. What have we learned from more than 50 years of shooting lasers at the moon? We now know that the moon is spiraling away from Earth at 3.8 centimeters per year, precisely as tidal theory predicts. We have measured subtle oscillations in the moon's rotation, called physical librations, that reveal information about its internal structure. And we have confirmed that the moon likely has a fluid outer core and possibly a solid inner core, based on how it wobbles and responds to tidal forces. Laser ranging has also provided stringent tests of Einstein's general theory of relativity. The moon and Earth fall toward the sun together, and any difference in how they respond to gravity would show up as anomalies in the laser ranging data. No such anomalies have been detected, confirming that general relativity accurately describes gravity even at these large scales. While laser ranging provided continuous monitoring from Earth, a new generation of lunar orbiters revolutionized our understanding of the moon's interior. Chief among these was the Grail mission, which placed 2 small spacecraft into lunar orbit in late 2011. Named Ebb and Flow by students at a Montana elementary school, the twin Grail spacecraft flew in formation around the moon, constantly measuring the distance between them with extraordinary precision. As they passed over regions of different density, the subtle variations in lunar gravity caused their separation to change by as little as 1/10 of a micron, roughly half the diameter of a human hair. By tracking these minuscule variations over 9 months of operations, Grail produced the most detailed gravity map ever made of any celestial body. The map revealed features invisible to optical cameras, the structure of impact basins beneath the surface, the thickness of the lunar crust in different regions, and the enigmatic mass concentrations, or mascons, that had puzzled scientists since their discovery in 1968. Mascons are regions of anomalously high gravity associated with large impact basins. Grail data, combined with sophisticated computer models, finally explain their origin. When a massive asteroid strikes the moon, it excavates a crater and causes the denser mantle material beneath the crust to rise upward. As the crater floor rebounds and lava fills the basin, the combination of uplifted mantle and dense basalt creates a region of concentrated mass, a gravitational anomaly that can affect the orbits of spacecraft passing overhead. Grail also discovered unexpected linear features in the gravity data, evidence of ancient rift valleys where the lunar crust was pulled apart early in the moon's history. These rifts suggest that the moon actually expanded slightly as it cooled, a counterintuitive finding that supports models in which the lunar interior was initially cold at its center, consistent with formation from a debris disk rather than slow accretion. The new millennium has seen a renaissance of lunar exploration, with spacecraft from multiple nations orbiting and landing on the moon. India's Chandrayaan-1 and Chandrayaan-3 missions have contributed scientific instruments and demonstrated landing capabilities. Japan's Selene spacecraft mapped the moon in unprecedented detail, and China's Chang'e program has achieved milestones that even Apollo did not accomplish. In December 2020, China's Chang'e 5 mission landed on the lunar nearside, collected approximately 1.7 kilograms of soil and rock, and returned them to Earth, the first lunar sample return since the Soviet Luna 24 mission in 1976. Analysis of these samples revealed basaltic rocks just 2 billion years old, much younger than any samples collected by Apollo, demonstrating that volcanic activity on the moon continued far longer than previously believed. Even more remarkably, in June 2024, Chang'e 6 accomplished something no mission had ever done before. It collected samples from the lunar far side. Landing within the South Pole Aitken Basin, the oldest and largest impact structure on the moon, Chang'e 6 gathered nearly 2 kilograms of material and returned it to Earth. Scientists around the world eagerly await the opportunity to analyze these samples, which may contain fragments of the lunar mantle and clues to the early differentiation of the moon and the differences between its 2 hemispheres. Meanwhile, the Apollo samples themselves continue to yield new discoveries. Modern analytical techniques can detect elements and isotopes that were beyond the reach of 1970s instruments. In 2019, NASA opened sample containers that had been sealed since Apollo 17, preserving pristine lunar material for analysis with technologies that did not exist when the samples were collected. These continued studies have refined our understanding of the lunar interior, the history of lunar volcanism, and the origin of the moon itself. The water found in volcanic glass beads, discussed earlier, was discovered through analysis of Apollo samples using instruments far more sensitive than anything available during the Apollo era. In 2023, India's Chandrayaan-3 mission successfully landed near the lunar South Pole, carrying a new laser retroreflector provided by NASA. This instrument, smaller and more precise than the Apollo reflectors, extends the network of ranging targets on the moon and promises even more accurate measurements of the Earth-Moon distance in years to come. The moon remains a scientific laboratory, a testing ground for technology, and a stepping stone for future exploration. Half a century after the last astronaut left, we are still learning from the Apollo legacy, still firing lasers at reflectors placed by human hands, still analyzing rocks brought back across the void of space. The mission continues. Science is not a collection of settled facts, but an ongoing conversation, a process of proposing ideas, testing them against evidence, and revising our understanding when the evidence demands it. The giant impact hypothesis has achieved broad acceptance as the explanation for the moon's origin, but it is not without competitors, complications, and unresolved questions. As we approach the end of our journey, let us consider some of the alternative ideas and lingering mysteries that continue to challenge lunar scientists. One persistent puzzle is the striking asymmetry between the moon's near side and far side. The near side, the hemisphere we see from Earth, is dominated by the dark Maria, vast plains of solidified lava that fill ancient impact basins. The far side, photographed for the first time by the Soviet Luna 3 spacecraft in 1959, is almost entirely highland terrain, heavily cratered, but with very few Maria. Why should the two hemispheres be so different? The crust on the far side is significantly thicker than on the near side, making it harder for volcanic magmas to reach the surface and fill impact basins. But why is the crust thicker on the far side? The giant impact hypothesis in its standard form does not obviously explain this asymmetry. One intriguing possibility is the multiple impact hypothesis, which suggests that more than one large body struck Earth, or that the moon-forming debris disk generated more than one satellite. In this scenario, a companion moon may have formed alongside our moon, orbiting in a stable configuration for millions of years before eventually colliding and merging with its larger sibling. Martin Utzi and Eric Asfaug proposed in 2011 that such a collision could explain the lunar asymmetry. If a smaller companion moon, perhaps 1/30th the mass of our moon, struck the larger body at a relatively low velocity, it would not create a crater, but rather splash across the surface, adding an extra layer of crustal material to one hemisphere. The impact would have pushed the molten magma ocean toward the opposite side, concentrating the creep-rich layer beneath the near side and creating the conditions for the extensive volcanism that produced the Maria. This secondary impact hypothesis remains controversial, but it illustrates how scientists continue to refine and complicate the story of lunar formation. The moon we see today may be the product not of one catastrophe, but of several. A body that has been reshaped by violence more than once in its long history. Another ongoing debate concerns the classification of the Earth-Moon system itself. Is the moon truly a moon, or is it more accurate to describe Earth and moon as a double planet? By conventional definitions, a moon is a natural satellite that orbits a planet, which in turn orbits a star. But the moon is unusually large relative to Earth, containing about 1.2% of the combined mass of the pair. For comparison, Ganymede, the largest moon in the solar system, contains only about 0.008% of the combined mass of itself and Jupiter. Moreover, both Earth and Moon actually orbit their common center of mass, the barycenter of the system. For most planet-moon pairs, the barycenter lies well within the planet, so it makes sense to say the moon orbits the planet. But the Earth-Moon barycenter, while still inside Earth, is relatively close to the surface, about 4,600 kilometers from Earth's center. Some researchers argue that this unusual configuration makes the Earth-Moon system more like a binary planet than a typical planet-satellite pair. The distinction is more than semantic. If large moons like ours are common products of giant impacts in the late stages of planet formation, then many exoplanetary systems may contain double planets rather than planet-moon pairs. Understanding the Earth-Moon system in these terms could have implications for the search for habitable worlds elsewhere in the galaxy. Many questions about the Moon remain unanswered despite decades of study. What exactly happened to Theia? Did it contribute significant material to the Moon, or was most of its mass absorbed by Earth? The isotopic evidence suggests extreme mixing, but the details remain unclear. How did water survive the Moon's violent birth, or was it delivered later by comets? The water locked in volcanic glass beads points to an interior that was never completely desiccated, but the mechanisms that preserved or delivered this water are still debated. What happened to the Moon's ancient magnetic field? Paleomagnetic studies of lunar rocks indicate that the Moon once generated a magnetic field, perhaps comparable in strength to Earth's, between about 4.2 and 3.5 billion years ago. But the Moon is too small to sustain a core dynamo for long, and the field eventually died out. Understanding why the field existed and why it disappeared could tell us about the thermal evolution of small planetary bodies. These questions, and many others, await future exploration. NASA's Artemis program aims to return humans to the lunar surface in the coming years, landing astronauts near the South Pole where water ice may be accessible. Human geologists on the Moon could accomplish in hours what robotic missions take months or years to achieve, selecting samples with trained eyes, responding to unexpected discoveries in real time, and deploying instruments too complex for robotic systems. Planned sample return missions, both crewed and robotic, will target locations not visited by Apollo, the polar regions, the South Pole Aitken Basin, and sites on the far side. Each new sample has the potential to transform our understanding, just as the Apollo samples did half a century ago. The Moon is Earth's closest neighbor in space, yet it retains mysteries that we have barely begun to unravel. It is a time capsule from the solar system's earliest days, a laboratory for planetary processes, and a stepping stone to destinations beyond. In studying the Moon, we study ourselves, for the Moon is literally made of Earth, flung into space by a collision that could have destroyed our world, but instead helped shape it into a home for life. We have traveled a long road together, from the myths of ancient civilizations to the laboratories where scientists analyze lunar samples with instruments that can detect a single water molecule. We have witnessed the birth of the Moon in fire and violence, watched its magma ocean cool into a crust of ancient rock, and traced the slow dance by which Earth and Moon have shaped each other across billions of years. Now, at the end of our journey, let us step back and consider what it all means. The Moon exists because of a catastrophe. Approximately 4.5 billion years ago, a world the size of Mars slammed into the young Earth with enough force to liquefy both bodies, eject trillions of tons of rock into space, and set our planet spinning fast enough to have 5-hour days. By any reasonable measure, this was a disaster of cosmic proportions. And yet, without that disaster, we might not be here. The collision gave Earth its unusually large Moon, a companion massive enough to stabilize our planet's axial tilt and create the consistent seasons that have allowed complex life to evolve. The massive tides of the early Earth may have concentrated the chemicals needed for life's origin, mixing the primordial soup in which the first organic molecules formed. The slowing of Earth's rotation, caused by tidal friction with the Moon, turned our world from a violently spinning top into a planet with days and nights long enough for photosynthesis and rest. The Moon is not an accident that happened to our planet. It is part of what makes Earth, Earth. This realization has profound implications for our search for life elsewhere in the universe. When we look at distant stars and their planets, we are beginning to ask not just whether those planets are in the habitable zone, but whether they have moons, and whether those moons play the same stabilizing role that our Moon plays for Earth. Astronomers have searched for exomoons, natural satellites orbiting planets around other stars, using the same transit techniques that have revealed thousands of exoplanets. So far, no exomoon has been definitively confirmed, though several candidates have been identified. The challenge is immense. Exomoons are small, faint, and easily confused with other signals in the data, but if our solar system is any guide, exomoons should be common. Jupiter has 4 large moons and dozens of smaller ones. Saturn has more than 140 known satellites. If giant planets in other solar systems have similar retinues, then exomoons may actually outnumber exoplanets in the galaxy. Some of these exomoons could be habitable in their own right. A moon the size of Earth, orbiting a Jupiter-sized planet in the habitable zone of a sun-like star, would receive the same amount of stellar radiation as Earth. It would be tidally locked to its planet rather than to its star, giving it a day-night cycle determined by its orbital period rather than permanent hemispheres of light and dark. Tidal heating from its massive host planet could provide additional energy, perhaps sustaining liquid water even beyond the traditional habitable zone. Our moon is a guide to what is possible. A proof of concept that large satellites can form through violent processes and persist for billions of years. When we eventually discover exomoons around distant worlds, we will understand them better because we have studied our own moon so thoroughly. The moon also reminds us of something that is easy to forget in our daily lives. We are part of a cosmic story that stretches back billions of years and will continue long after we are gone. Look up at the night sky on a clear evening. There it is, that pale silver disk, rising above the trees or buildings of your familiar landscape. It is so ordinary, so constant, that we hardly notice it most of the time. But it is also a world, a place with mountains and valleys, craters and plains, where human beings have walked and left their footprints in the dust. Those footprints are still there, preserved in the vacuum where no wind blows and no rain falls. They will remain for millions of years unless disturbed by meteorites or future visitors. They are monuments to what humanity can achieve when we set our minds to seemingly impossible goals. From Galileo's first telescopic observations to the boot prints of Apollo astronauts, the moon has been a mirror in which we see ourselves. It has challenged us to understand the heavens, dared us to reach beyond our atmosphere, and taught us about the cosmic processes that made our world. It is a laboratory, a time capsule, a destination, and a constant companion. The story of the moon is not finished. NASA's Artemis program aims to establish a sustainable human presence at the lunar South Pole, where astronauts will search for water ice and demonstrate technologies needed for missions to Mars. China, India, Japan, and private companies are all pursuing their own lunar programs. In the coming decades, the moon may become not just a destination for explorers, but a stepping stone to the wider solar system, a place where humanity learns to live and work beyond Earth. We are living through a new era of lunar exploration, one that builds on the legacy of Apollo but aims to go further and stay longer. The moon that our grandparents watched through binoculars may become a place where our grandchildren live and work. And somewhere in the distant future, humans standing on the lunar surface will look up at the blue-green Earth hanging in the black sky and wonder at the cosmic chain of events that led them there. They will know that the moon beneath their feet was born from a collision so violent that it nearly destroyed both worlds. They will know that the Earth above them was shaped by tidal forces from the very ground they stand on. They will know that life itself may owe its existence to the dance between these two worlds. They will be part of the story that began 4.5 billion years ago and continues still. So the next time you step outside on a clear night and see the moon shining down, take a moment to appreciate what you are seeing. That silver light has illuminated every moment of human history. It guided our ancestors across oceans and inspired their myths. It drew Galileo to his telescope and Apollo astronauts to their spacecraft. It is a witness to all that we have been and all that we might become. The moon is not just a rock in the sky. It is a partner in our existence, a consequence of cosmic violence, and a reminder that the universe is stranger and more wonderful than we can easily imagine. Thank you for joining me on this journey. If you found this exploration of the moon's origins enlightening, please consider subscribing to Deep Calm Science and sharing this video with others who might appreciate it. Your support helps us continue to explore the wonders of our universe together. Until next time, keep looking up.